Welcome to KINDLEVAN PDR.
We're recording? We're recording.
I've been recording.
I'm Ben,
I'm Cisco.
and we're here to talk about KINDLEVAN, our competition entry for IREC 2026. You know, Ben. There you go. See you on there.
Okay, this is it.
Yes. So this is the schedule for today. We're starting at 12:10. We're going to do 5 minutes of background, 20 minutes of systems. Then we're going to go into the mechanical, payload, and recovery sections. After which we're going to have a quick 20-minute break, assuming that we're on schedule. Afterwards, we're doing electrical, avionics, and telemetry, and propulsion, with any final questions at the end. And then if you guys have any questions just throughout the presentation, before we skip to the next slide, feel free to shout them out, grill us on any design decisions, and we can keep on going from there. So yeah, about the team, we're around 45 regular members, founded back in 2018, and we have almost 100 launches to date. Hopefully we'll get to that triple-digit mark next spring, which is really exciting. The projects include doing individual certifications, which involve L1, L2, L3 certs, a hybrid motor development program, and of course, competition, which is why we're here.
So our Team Rocket program is organized into sub-teams. The mechanical team is all the structural analysis components, the electrical, and then avionics and telemetry, do all the electronics and flight computer stuff. Recovery is in charge of parachutes, deployment and recovery, successful recovery of the rocket, propulsion, in charge of motor liftoff, and payload in charge of the scientific experiment that we're housing inside of a rocket.
So we have a couple goals for this design review. We're going to talk about KINDLEVAN, our vehicle for the competition, sufficiently in depth to the point where we can have conversations about anything that we might be missing or kind of demonstrate our work so far in the year. We want to identify risks and propose mitigation plans. And we want to talk about each individual subsystem and talk about its level of maturity. Finally, we want to review plans and analysis before beginning our manufacturing process in the spring semester. Just want to make a note that certain subsystems are further along than others, and there is still open work that we're going to talk about at the end of each section. And where it's possible, we hope for you guys to chime in and help us clarify if we're not clear about certain things that we're doing. And hopefully by March next year, after the first flight test, we want to do a critical design review, which will basically be building off on this and talking about our post-flight learnings and the final steps that we need in order to be ready for competition in June.
Ben, sorry to interrupt. I have a quick question. If we have questions on a particular section, do you want us to wait until like the end of that section in case it's stuff that's like, oh, we know this, but we're looking into it, or does it not matter?
If you can talk about it at the end of that slide. So for example, if we're talking about mechanical and we're talking about one particular bulkhead and your question is about that bulkhead, you can chime in whenever we're done with that slide. If it's more about like the electrical PCB as like a whole, then maybe wait till the end of that section. But it's kind of up to your discretion. Feel free to butt in at the end of a slide whenever.
Okay, sounds good, thanks.
So a little overview of KINDLEVAN as a whole. This is the Tufts Rocketry 4th Team Rocket. Started at the beginning of the semester, and our final launch and end of project is the IREC competition in June. KINDLEVAN stands for Kinetic and Dynamic Legendary Vertically Ascending Novelty. And then so the purpose of the project is our 2026 IREC submission. Yeah, and so as we work through our project, we're adding technical documentation, these progress reports, and we're adding to our Notion.
And what is the competition? In 2026, in June, we're going to IREC, which is the world's largest intercollegiate design, build, fly rocket competition in the world. It's projected to be June 15th through 20th, with the launch days being 18th, 19th, 20th, maybe 17th. We're trying to launch early in that and hopefully basically be ready to hit the pads the second we get there. It's managed by ESRA, which is the Experimental Sounding Rocket Association, and we're competing in the 10K COTS category, which is going to be a commercial off-the-shelf solid motor. The goal, of course, is to carry a 2 kilogram 2U CubeSat form factor to 10,000 feet above ground level and then safely recover. To do this, we're going to be utilizing SRI computers and an air brake system to induce aerodynamic braking, which should slow our ascent to reach a precise 10,000 foot apogee.
So some key definitions that we'll be using throughout the presentation are COTS, commercial off-the-shelf, which for our purposes, those are our flight computers, motor for the rocket and for the servo, and any purchased components or modifications allowed by the manufacturer. But then SRAD is student research and developed, with major modifications to purchased components or any components that we build and in-house ourselves. DTEG stands for Design, Test, and Evaluation Guide. This is the document that ESRA provides for guidelines for the competition, for safety, and all requirements for our design and flight that we have to follow for the competition. And then IREC is the International Rocket and Engineering Competition that we are building this rocket to participate in.
And then throughout the presentation, at the end of each section, you're going to see a standardized risk matrix, which is basically our way of identifying some of the risks that we need to mitigate throughout the year. In the y-axis, you can see the likelihood that we anticipate each of these risks being 33%, 10%, 1%, and 0.1%. The higher it is, the more likely we believe this kind of risk is going to happen. On the x-axis, we're going to have the impact, which is denoted 1 through 5. 5 being the most critical kind of impact, which can involve loss of mission, injury to members, a lot of stuff that we really don't want to happen. Whereas the 1 is stuff that, if it were to happen, it would be less of a high damage. It would be more of a loss of data, but nothing terribly damaging. And then the colors each denote the kind of how bad each thing will be. So when you look at the likelihood and the impact, the red sections are things that have a higher likelihood of happening and would be really bad, whereas green is stuff that might not happen and is less bad if it were to happen. And then each subsystem is going to be using one of these at the end of the section to talk about what kind of risks that they anticipate.
So now that we've done like an introduction to this presentation, we'll do a systems overview of the specifics of this project.
So we're going to talk about the carryover from our past team rockets to this year's team rocket. On the right side, you can see a really nice graphic of CARM and Hodge, which were our competition entries for 2024 and 2025. As you can see, over the years, our design has changed. The colors of the rockets have changed. And yet there are a significant number of carryovers or things that we have continued to do from previous rockets. For example, last year we used a removable fin design, which were the shiny metal fins at the bottom of Hodge. This year we're going to continue doing that, except it's going to be fully removable, as in only one set of fins. Once again, from Hodge, we're going to be reusing a universal factor of safety goal of 1.5. And then similar to the past 2 rockets, we're also going to be doing composite and aluminum construction for the most part. The flight profile is going to look very similar to the previous 2 rockets. Per IREC rules, we're going to have redundant COTS ejection electronics. And although our payload mounting method has looked different every single year, the location that we're mounting the payload is very similar to Hodge's. Our thrust plate and motor retention methods are going to be the same, using a COTS retainer on a machined aluminum thrust plate. Our AVBA internal design is going to look very similar to Hodge's. And finally, the forward chute separation will be just below the nose cone, similar to Hodge's design.
So some areas of improvement from our last year's design. Number one is our fin design. Last year we had just one component of swappable fins and one set fixed fins, and this year we're doing the entire fin assembly is or the entire set of fins is completely replaceable. And then the avionics bay layout. Last year there was a huge improvement from Garmin, but still our integration had some difficulties. And some sections were inaccessible through even the hatches. So this year we're going to have better wire management, better accessibility on and off pad, and just streamline everything where possible. Material testing last year, we had inconclusive epoxy shear test results, whereas this year we'll use correct ASTM lab shear testing standards. And then apogee control last year, we had dynamic fin geometry control to induce drag, but we still had inconsistent where the motor performance was came into play. But this year we have air brake deployment to actively control the altitude that we reach. And then our payload last year was testing basic vibration tests of electrical components. And this year we're going to have test some solar cells efficiency throughout our flight path, specifically on descent and increase of air density. And then we're also going to have an ease of use or ease of integration. Last year there were no common fasteners, and it required many tools and bolt sizes to integrate. And then this year we're going to have common fasteners and to use a Phillips and 632 bolts wherever possible.
This is a continuation of our areas of improvement. In the recovery sector, in Hodge, we use black powder energetics. However, there's an issue where at higher altitudes, black powder combusts more weakly just due to less air. And then we also use nylon harnesses using a Kevlar cord protector, which was really a pain when it came to integrating. So this year we're going to be using CO2 as both primary and backup for both events. And then Kevlar harnesses ideally will prevent need of a Kevlar cord protector and should be much nicer on integration. The Hodge camera mounts disrupted the flow over the airframe and had no cooling vents, resulting in a lot of overheating. This year we're doing a lot of camera mount streamlining to make it less intrusive in the outside flow, and then hopefully taking the best advantages possible of the natural convection on the launch pad. That way we don't have an issue where the cameras are going to start overheating before we even start flying. The computers last year were 2 SRAD boards collecting telemetry data, but we only were able to get flight collection in one of them. This year we're going to be using SRAD again, but we're going to be using that for the primary energetics as well. And we hope to get successful data collection on all sensors on our SRAD boards. We had a flight test early this November, or last month in November, and we are on the right track to getting that again for our competition launch. Finally, no live transmission or data collection of telemetry, which we hope to have live data this year, which is really exciting. And finally, the dashboard, once again, we had no telemetry collection. This year, we want to have a nice interface to see in-flight data as it happens.
So an overview of the external components of our vehicle. We have from forward to aft, we have the nose cone and the forward airframe going into the switch band of the avionics bay with a coupler tube 6 inches on either side. And then we have the air brakes at the top of the booster section with removable fins in the aft section. And motor components, and the entire diameter is 6.17 inches and the length is 118 inches with a dry mass of 43.9 pounds. And then our internals, we have the payload mount in the nose cone section, housing or mounting the payload in the forward section, and which is in the component for the drogue parachute. And then in the avionics bay, we have all of the internals with the electronics and the the recovery energetics on either side of the bulkheads. And then we have going in the aft section, we have the main chute, and the air brakes are in the booster section with its own little mini avionics bay for the air brakes. And then, of course, the motor mount and the removable fin attachments will go through the wall in the booster section.
So we use OpenRocket to do a lot of our simulations of the rocket. This is kind of just a screenshot from our OpenRocket design, and it helps with a lot of the layout, again, especially in the preliminary design phases. You can see this is kind of the same layout as what Cisco was just talking about, where we have our parachute compartments, the drogue in the forward, the main in the back, and then we have our payload located there. Using the simulation, we can get a lot of stability characteristics and a lot of our trajectory data. And this is what we use to figure out what kind of apogee we're shooting for. And I just want to talk a little bit about some of our air brakes design decisions since our entry to the competition, just while I have the OpenRocket up. We had a lot of trouble trying to determine how the center of pressure is changed by the air brake position. Initially, when we first applied to the competition, we had the air brakes in the avionics bay coupler tube, which would allow, in the switch band with the motors in the coupler tube. And this would allow us to use one set of computers and not need to have a second set of redundant computers to control the air brakes. The issue of this was stability is basically calculated by the distance between your center of gravity and your center of pressure. And when you have your air brakes further forward in the airframe, we noticed that as you deploy air brakes, your center of pressure moves forwards and you lose stability. A lot of teams in past years have had trouble characterizing how much your center of pressure moves. And so they just decided to move it as far back in the airframe as possible. And with this idea, we decided to move it into the booster airframe, which warranted a new assembly design, which the mechanical team will talk a little bit about. But essentially, the way that we know that our stability is not going to go below the allowed 25% margin is basically due to a worst case scenario. You can see plotted in the blue is the center of gravity initially on takeoff, and then the center of gravity after motor burnout, once the motor loses all that mass and the center of gravity moves forward. It moves from 74.3 inches from the nose cone to 68.8 inches from the nose cone. The center of pressure starts off at 85.3 inches. And in an absolute worst case scenario, as the air brakes are deployed, the center of pressure would move up at most to 82.5 inches from the nose cone. Using the calculations for stability in terms of caliber and percentage in the bottom right, you can see that stability before launch is 1.8 cal and 9.6%. And the stability after air brake deployment is at minimum going to be 2.3 cal and 11.5%, which is above the minimum allowed stability for the competition. This way, we know that although we still need to do some simulations in terms of coefficient of drag and coefficient of drag, basically we don't need to worry about our stability on deployment using this flow of logic.
So just concept of operations, Juliana will go into more detail about this, but throughout the flight, we have avionics arms on the pad, and then we have liftoff, motor burn, and then we have motor burnout at about 1,700 feet. And then on the ascent after motor burn, we have air brakes deploy after an altitude of 6,000 feet. And then at precisely 10,000 feet, we have apogee and drogue deployment, which drogue deployment will occur in the forward section, which Juliana will also talk more about. Oh, shoot. And then we have main descent. Oh, after drogue descent, we have payloads initiation of data collection of the solar cells. And then we have main descent at around 1,400 feet, and then recovery.
Here are our testing and flight plans. We plan on having a test flight in February 2026. This is going to be a mid-altitude flight of just testing the airframe and the recovery systems. We're going to be using content electronics as the primary, and the payload structure will only exist for our load path. We don't expect the air brakes to be ready to fly and to be active, and we don't expect the payload to be collecting data quite yet, but we need these to be integrated just for the structure of the airframe itself. For flight test 2 in April, we want to do a high altitude flight test of SRAM electronics and finalized design. And we hope to have the air brakes and the payload ready to go during this flight test in case anything goes wrong. That way we don't have an issue where the first time we're testing active air brakes and payload in an actual flight ends up being the competition. Throughout the semester, we also plan on using L1s and L2s to test electronic components. And then hopefully in June, we will be launching at the competition. In the past, I guess last year, we had no flight tests due to rain. And then the year before, we had 3 flight tests. And we found that our 3rd flight test had a high risk of, well, I guess the issue was it was too close to the competition flight. And if something goes wrong, as it did 2 years ago, where we got stuck in a tree, it would result in a lot of reconstruction needing to be happened like at the competition itself. To mitigate that, we're reducing our plan to just 2 test flights, and hopefully this will collect all the data that we need. Of course, there's always a risk of not having any test flights, similar to last year where it just rained constantly. In this scenario, we have mitigation plans. We plan on doing a lot of ground testing to see as much validation of our subsystems as possible.
Quick question on that, Ben. In the case that you're only able to have 1 test flight, what's the plan for the air brake configuration?
It depends on when the test flight is. If we just have a February test flight and that's it, we're going to be doing a lot of hardware in the loop and ground testing of the air brakes. And then we're going to have to make a last-minute decision on if our ground testing is able to validate what we anticipate will happen during an actual competition flight. If it's only 1 launch in April, then we hope to be flying with everything active. That first flight test is more so just to make sure the airframe and recovery system is all in place and ready. But we have pretty high confidence that that will be the case. So I'm hoping if one of them were to get canceled, it would be the early one. But here's to hoping that both of them end up happening.
Yeah, I hope that works out. Yeah, I agree with the high confidence in recovery system stuff. Is there any plan to fly the mechanical structure of the air brakes, like with no control on the February test flight, or?
Yes. So the way it's designed is the air brakes do not need to be flown active, and they can actually be, so part of the assembly, which you'll learn about later, is included in the load path. So they will need to be physically in the airframe in order to fly. That being said, we have plans on starting to build the air brakes very, very early on in January, or very early on in the semester once we get back from break. And we plan on doing ground testing of the air brakes as soon as possible. So even if they're not active in that February flight test, they will physically be inside the rocket.
Okay, perfect. Nice.
So for flight test 1, some of our targets, our main goals are to just validate the airframe and the recovery system in our simulations. The recovery system, the flight test is extremely crucial because we have swapped the main and drogue deployment positions. So one of our main concerns for recovery is early separation of the booster and the forward sections, meaning early deployment of the main parachute. That's because of the increased mass of the aft section when the drogue deploys. We've accounted for that with the number of shear pins, but flight test will be crucial for that. So we have systems, just minimum validation requirements, just all checklist functional and complete. And then for mechanical, we want the rocket to remain intact throughout the landing and target no permanent airframe damage. Electrical wiring is secure and functional, and pre-launch UI improves from the 2025 launch. And then for avionics, we want Panini to record onboard data and Our target is to have download and GS display. And then for recovery, we want the vehicle to be recovered in adequate condition, and our target results are to have no tangling of the chute or the harnesses, and for no damage to come to the rocket airframe at all, or the payload. For propulsion, we want the motor performance to be completely nominal and remain fully retained. And then for target results for propulsion, we want successful post-flight removal from the case. And then for our payload target minimum validation requirements is for the payload mount to withstand the recovery load, and then we want it to both withstand the load and to collect data if the payload's ready. And then lastly for media, we want functional external onboard cameras and epic footage.
How
So
many
these are
cameras?
Sorry, go ahead.
How many cameras?
Only 4, unfortunately. I was trying to push for 8.
Hear that?
4 is a lot. 4 is a lot. I'll be happy.
They're small.
As long as I get the job done.
It'll be pretty. Yeah, these are our simulation parameters that I've been using in OpenRocket. These come straight from the ESRA IREC design, evaluation, testing guide. So we have average wind speed, standard deviation of the wind speed, turbulence, direction, temperature, pressure, latitude, longitude, altitude, rail length, and angle. And this is kind of how that compares to St. Albans, Vermont, which is where we plan on doing both of our test flights. As you can see, the biggest change there is the temperature, as we will be very, very cold in St. Albans and very, very warm in IREC. Also, altitude will be different, but besides that, and the rail length is different. That being said, we have full confidence in both of these test flights and both these test flights and both these launch sites, and we are excited to be launching at both this coming semester.
So for our flight test 1, we are going to test on an Aerotech L2220, reaching an apogee of 4,800 feet, and adequate thrust to rate ratio, rail exit velocity 63 feet per second, which we believe to be fine. Stability of 2.38 calibers, reaching Mach 5.5 or 0.55. And 12 Gs, and with the parachutes that we've chosen, we've got an 81 feet per second and 21 feet per second under drogue and main respectively. And then our flight test 2, we're flying on the Aerotech M2400 with reaching an apogee of 7,700 feet. Both of these were chosen to test at varying altitudes. And we have a rail exit velocity of 79 feet per second there, reaching a higher acceleration of 0.76 Mach 0.76, and only 9 Gs. And then our descent velocity will have 96 feet per second under drogue and 23 feet per second under main. And then for our IREC competition, we're flying on the M3400. Ellen will go more into the reason behind choosing this motor, but we're hitting an altitude of 10,727 feet. We want to overshoot the 10,000 feet significantly so that we have enough room for air brakes to slow the rocket to 10,000 feet. We also have rail exit velocity of 103 feet per second, which is well above the 82 feet per second minimum by the IREC DTEG. And then stability of 1.79 calibers, which I believe is like, 11% of the rocket length, which they require 7%, 7.5. We've got Mach 9.59, and acceleration of 13.9 Gs. And then under drogue, 94 feet per second, 94.68 feet per second, and main 23.62. And all of the other subteams will go into more detail on analysis of our confidence in our ability to fly at Mach 9.59 and 13 Gs or 14 Gs.
And then here's our risk matrix of the systems side of things. You can see we have a few likelihoods that are in the level 4 impact, which I'll talk about in a sec. We have one that's in a level 5 impact, but a very low chance of happening. And then we have two other ones in the yellow region. Number one, the first risk is a major schedule slip. This can happen for a couple of reasons. And this could be bad, as in we won't be ready for the competition. So in order to mitigate this risk, we're going to set reasonable goalposts and stick to them. And then if needed, we will skip test flights. So like I mentioned before, our first February test flight, if we're not ready by then, it's okay if we don't launch, but we need to make sure we're back on track and able to launch for that test flight in April. The second risk would be a test flight failure. This has happened before, 2 years ago when our headlines were cut and we had a hard landing. To mitigate this risk, we're going to produce easy to replicate parts and test thoroughly before the flight. Like I mentioned before, a lot of our hardware in the loop and ground testing for the air brakes will involve this. And then we're going to have spare parts and materials at the ready at the launch site. There's a risk of the payload structure not being ready for that first test flight. In order to mitigate this, we're going to invest heavily and early in the payload structure design, and the mechanical team will be able to provide certain support to the payload team if need be, so that we're ready to fly for that first February test flight. Finally, we have a risk of insufficient funds. This I'll talk about in a few slides, but basically, we contain hardware development program descope options. So if there's something that we can test slightly less thoroughly, but have the funds to actually compete in competition, we will do that. And we are prepared to make difficult cost-cutting measures for competition travel if need be. Risk number 5 is the sub-team lead is unable to fulfill properly their duties. To mitigate this, we're going to be identifying deputy sub-team leads, maintain a good leadership level understanding of all sub-team operations, and be able to provide that help if need be. Risk number 6, injury to team members. We're going to be using appropriate PPE and follow all the safety guidelines at all times. This is especially important when coming to epoxy curing and composites work and anything that can risk harm of our team members. Finally, we have a risk of payload internals not being ready in time for the competition. Like I mentioned before, similar to structure, we're going to be providing additional support to the payload team. And if need be, we can simplify the experiment. However, we have a pretty good grasp on what we want to do, and we feel confident that it will be ready for competition.
So our current open issues, one of the major ones are our air brake deployment, effect on our center of pressure, but it has been extremely mitigated by our positioning of the air brakes with the center of gravity, as Ben was explaining earlier. With air brakes, we also have active computation for air brake control are being researched at the moment. But we're trying to figure out if we want to have air brake controls versus preset parameters, or air brake computation, active computation versus preset parameters. Electronics and avionics will talk more about that. For motor, we have that our chosen motor, the M3400, if it's a pretty high velocity, again, Mach 9.96.
Yeah.
59.
It goes fast.
Yeah, not all effects have been considered, but we're working to have confidence in high velocity. Another concern is that motor is out of stock on the Aerotech and Wildman website, but we're working to contact sourcing for that people to source the motor for IREC. Also, sad, many of our leads are not going to be here next semester and going abroad, but we have people to take their place. And then we also need a fully detailed schedule before manufacturing begins next semester, but more on that later.
Some of our lessons learned this past year, especially when it came to the design, integration, and launch of Hodge, was that optimization and ease of integration is a very delicate balance. I have a distinct memory of this last June. We were trying to integrate the payload structure, and we had used 2 different size bolts for a factor of safety increase that was negligible. This is why one of our biggest pushes this year are to have common fasteners wherever possible, which are going to be that Phillips head 632 bolt. We want to do a lot of system integration testing and practice, because when it comes to pre-launch operations, having everyone know what they can do and how they can help to get that rocket off the pad is super important. Similarly, early integrated testing is crucial, and we always want to follow our checklists. Having our sign-offs are really important when it comes to making sure that everything is ready for launch. When we come to a launch, we want to have extra stock material and tools on hand. Our November launch, unfortunately, was our only launch this semester due to weather, but we had some issues with not having the right tools on hand and having to scramble to find solutions. So making sure we use our packing lists is going to be super important, especially when it comes to the competition launch. We found that it can be difficult to focus both on our team rocket program and our level 1 and level 2 rocket program. And we've actually taken some steps to have open office hours to kind of mitigate that conflict during our Sunday meetings. Do you want to talk about this one a little bit?
So, where was it? Now 2 of our launches have landed on or over water, which means that we want to either adjust our parachute deployment altitudes or launch angle wherever we can to steer away from water.
And thankfully, Midland, Texas doesn't have a lot of lakes or rivers, which we are very thankful for. Last lesson learned was launch schedules can slip due to weather. Last spring, it was rain. This semester, it was corn and fire. And we're really hoping that this coming spring, things will look a lot better in St. Albans, Vermont.
So a rough schedule to completion. We're gonna have the rocket design finished, meaning having finalized optimization and analysis of any structural system components. That'll be by the beginning of January. And then we'll have the structure completed and fabricated with all significant components, including the payload and the air brake structure by February, specifically before our first flight test. And then we want to have payload mission ready, meaning chassis complete, SY computers complete, and solar cells integrated by April, which we want to happen before flight test 2. And then also active air brakes. We want to have finalize our computer code and system fabrication before April 2026, or before our flight test 2 in April 2026 as well. And then we'll have our launch, and in order to do that, we need to stay on this schedule, which is in June, and for our competition flight.
This is kind of a breakdown of our budget needs. We need about 33,000 in order to compete and launch our rocket in June in 2026. Currently our budget is 25,900, and we've spent 1,300 so far. The reason we haven't spent much yet is we haven't traveled to too many launches. We just had one in November, and a lot of our purchases so far have been testing, specifically for like material testing and early PCB design. Good news is, you can see our breakdown here, our launch vehicle is fully funded. However, we need some additional funds in order to compete in the competition. As you can see, almost about a third of our budget is just for the competition, including fees, travel, and lodging. And we estimate we need around 7.5K just to compete at IREC. Our plan for this so far is to advocate to TCU. We have bookmarks where we have a pretty high confidence that we'll get a good amount of this money, and we have mitigation plans in case we don't get the full amount. And any additional funds are going to be able to reduce the trip costs for our members, both this year and roll over for future years. Any questions for system before we move on to mechanical?
Yes. Would you mind going back to slide 26, please?
Sorry, say that again?
Do you mind going back to slide 26, please? Thank you. Oh, I wrote down the wrong number. The slide before that. Oh, sorry. No, 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 no.
Oh, 27.
All right, let me just pull up the file. The slide where you're talking about the
What?
air brake altitudes. Um,
Oh, you want the ConOps?
yeah, the ConOps. Sorry about that. Slide 20. Um, yeah. My question on this was so supposedly flight simulations have an accuracy of plus or minus 10%, was the like number thrown out. I know we got like really good accuracy in the past on some of our open rocket sims, but plus or minus 10% on 10,700 feet apogee is what I have here. It's 9,600 to 11,800. Um, is there like, do you think from now until January when you finalize the design, there'll be like more of a push to try and raise the bottom end of that range, or are you comfortable and happy shooting for sort of not that high above 10,000, and hoping that there's like enough wiggle room for the air brakes, or are you gonna like try and push to raise that apogee so that the air brakes have more authority, but also like more wiggle room to be able to bring it down?
So we feel pretty confident in what we are aiming for right now. Historically, both of our previous team rockets have overperformed in motor performance, meaning that the apogee reached was higher than we anticipated. On top of that, our 10,700 is actually, in case we do overshoot, like you mentioned, we could see that being a bit higher than we anticipate our air brakes being able to account for. Because of that, we aimed for a motor that would overshoot with the suspicion that there would be a decent chance that the vehicle would end up being a bit heavier than anticipated. If the inverse is true, we have a backup motor, which we don't have the simulation in the systems, but Ellen will talk about during the propulsion section, where it's a slightly weaker motor, but it should lower apogee in case it goes too high. Obviously, there is a lot of variation when it comes to just launching a commercial off-the-shelf solid motor. So there's only so much anticipation we can do. But that's kind of why that 10,500 to 11,000 range was kind of selected.
In terms of error in our altitude that we actually reach, it's also taken into account with our computation ability for the actual air brake controls. So with more research on that, we'll have more confidence in our precise altitude that we're able to reach.
Do you have like a rough idea of how much control authority the air brakes have? Like by how much can they bring down the apogee? Like what's the most they could bring down the apogee if you just like deploy them to the max at 6,000?
Yeah, so we've done some very early simulations on that. Are you talking about that in your mechanical section at all?
No, but I can make a note during that section.
Okay, Sean will mention it during the mechanical section. But we anticipate being able to lower, I believe it was 600 to 1,000 feet. Totally dependent on when the air brakes end up being deployed. But in a worst case scenario, we anticipate around 1,000 feet being trimmed off of our apogee at most.
Okay, sounds good. So if you go to like 11,200, you'll still have the authority to bring it down to 10,200.
Of course, we'll learn more once we do more hardware in loop and ground testing. So that's kind of our main push when we come back from break.
Okay, nice.
Any other systems questions? Mechanical, take it away.
Oh, and also just continue to shout out questions as they come. Right now, we can't see any of you guys, so if you raise your hand, we will not see it. So just shout it out. Without further ado, mechanical.
For the mechanical team, we'll be going over about an hour, give or take, of all sorts of fun stuff.
Yeah, I'm Sean.
I'm Sheelan.
I'm Missy.
Yeah, we're the mechanical leads. So first, a little design overview. So some of our main components that we have an airframe that's capable of withstanding the loads that we are expected to take, and that includes speed, chute deployment, and all the recovery loads. We have mounting systems for all our various components, including the payload, air brakes, avionics bay. Let's just make sure everything is securely mounted. Air brakes, which are going to withstand the intended forces and hopefully be actually useful and able to bring our apogee down within our expected range. We adhere to all the IREC guidelines, so we've been looking at the design, test, and evaluation guide. That's kind of been our Bible during the design cycle. And we also have all our components fastened with shear pins, nuts, bolts, chute lines, and epoxy. This is our full CAD. So just some notable things. Going from top to bottom, we have the payload in the nose cone. Then we have our avionics bay. Moving down, the air brake assembly, and then the motor assembly with our removable fins.
So first, fin assembly, it's just going to be fiberglass motor mount tube, which will house our motor casing. Then our fins are going to be attached to fin mounting brackets, which are attached to the wall. They're made of aluminum 7075, and we're going to use 1101 epoxy to fill them in place and keep it all as rigid as we need it to be. And the removable fins will just be set into those aluminum mounting brackets with screws, and those will help us modify our apogee and then also replace them if they ever get damaged.
This is our thrust plate. So it looks pretty similar to the thrust plate in previous years. One notable change is we've added a fillet along the inner ring there. That's because we can use a wall, is that right? During the CNC manufacturing process. So it has a wall around the outside that we use to secure it to the airframe with epoxy, and it has grooved walls. Slots for the fins, a rail button, that little nub there you see is for the rail button, holes for the COTS motor retainer, and then this is our aft airframe bulkhead. This is the bulkhead that interfaces with the air brake assembly. So those 4 outer holes there are for the air brakes mounting. We'll kind of go into that assembly a little later. This design has been championed by Lucas here, so he's been working hard on getting this in. But yeah, so it has a U-bolt mounting hole, so it's going to take the load from the is that aft or main?
What?
Bottom.
The bottom.
Yes,
What's that?
aft. No, I mean
No,
Drogue or main?
yeah, main.
That's the main.
So it takes the main parachute load and then transfers it into the airframe. So there's nubs for to screw through the airframe into that bulkhead to secure everything. One thing, we don't actually need to have the air brakes installed. We could just have this bulkhead in and screw that in, and our load should be perfectly fine. It also has a O-ring groove around the outside. So because we will be removing the air brakes and it needs to slide and pressurize. So that's why we have the O-ring groove.
This is the avionics bay. It's a design basically reused from last year, except the center supporting bracket was reduced from 2 to 1, and that houses the electronics and the avionics systems. We're keeping our hatch design so that we can access the batteries and SD cards. But we still have an open issue for us is still wire management, which we never addressed last year either. But we'll definitely spend some time to manage that because we had some issues with them getting caught on the inside walls when we would slide this in last year. And then the avionics bay bulkheads are mounting points for the threaded rods that run through the center of it and have a sled mounted on it.
and they connect the app-based recovery harnesses via 516 U-bolt. And they also hold the CO2 canisters, which I think we're not using any black powder this year, but we're still gonna keep the Raptors for those as well.
This is our air brake assembly. So you can see that bulkhead on the top there with the from the parachutes. And it's going to be transferred directly into the walls through those nubs. So the actual air brakes shown on the bottom there shouldn't be taking any load from the parachute. They're attached to the bulkhead with, right now the design is to use 2 threaded rods, which are shown on the left and the right there, and then 2 standoffs. This is subject to change, but that's what we have right now. So it mounts in the app section, kind of where that bulkhead is. And the flight computers will hopefully be mounted on to those threaded rods. You can see the design is mostly finalized. We're using a rack and pinion design, which is out the air brake. But we haven't designed any of the mounting mechanisms for the motor or the flight computers or anything like that. So that's still an open issue. And we also need to do MBA on this system, make sure it can actually withstand the loads from the air brakes being deployed and from the drag created by those. So that's where we're at with the air brake CAD. And this is just a small bill of materials, all the stuff we're going to use. Go into every part specifically, but the room here.
So the first round of testing we did for material testing this year was tensile testing. The point of this was to inform our fin material decisions. We did similar testing last year, but this year we're not doing lap shears because they're fully removable. So we just wanted to create dog bone samples that would only be the raw carbon fiber, and that would allow us to determine the thickness of the fins. We used a standard test method for tensile properties of the polymer matrix materials, and the outputs we were looking for was the Young's modulus in the lengthwise and crosswise direction, because that can be subject to change for a composite, and Poisson's ratio and a stress strain curve. And then this information was fed into Ben's fin flutter calculator, and we were able to calculate an overall modulus for the carbon fiber based on the lengthwise and crosswise. And then using an equation that was found from the NACA technical paper 4197, this Excel or spreadsheet calculator allowed us to find factors of safeties for the varying thicknesses. And so you can see they're listed up there, and the one we decided to go with was 5/32 inch for a factor of safety of around 1.66. And that just reiterates what we did with those. The removable fin mounts will be made out of 3/32 inch aluminum 7075 this year, because they are stronger but lighter, so better strength to weight ratio. And yeah, that about covers that.
So beyond the fin material design, we decided to try and redo our lap shear tests. This is something that we tried to do last year, and it didn't work as well as we hoped. But this year we used a new model for the lap shear testing, and our goals were to get better shear modulus and like strength data on the bonds between aluminum fiberglass and fiberglass when bonded with 1101 epoxy. Because the data sheet for this epoxy only gives aluminum bonds. And for one, that's going to be significantly weaker than if it went bonded to fiberglass, which is what we can do. And 2, we just want more accurate information for when we're designing and analyzing our work. So the first goal was to get the better data. The second goal was to start to look into optimal bond prep work. So this was somewhat, BPS Space did a video on this, and we used some of his info, although I don't necessarily agree with all of his work, but we did 3 different bond prep methods. The first one was just isopropyl alcohol. The second one was at 10 seconds of acetone on a lint-free wipe, followed by cleaning with isopropyl alcohol. And the third one was sanding with fine grit sandpaper and then cleaned with isopropyl alcohol. Next slide. So these are our results. There's a lot of info on this slide, but we took from the instron force, displacement, tensile stress, tensile strain, and transverse strain over time. And then we also recorded the method of failure for each sample. So the bottom left, I believe that's the set of the 5 acetone samples that we did. You can see pretty well how they failed. And we also took down the area of overlap of the 2 samples. So it was supposed to be 1 inch by 1 inch. But in practice, the 1101 epoxy really likes to slip. So we measured each sample before testing it to find its actual surface area and of overlap, and then we normalized the data with that. So the 4 graphs, 2 of them are just the force that it was able to withstand, and the other 2 are the force normalized by the overlap area. So going forward, we still need to do some more work with the data to find the shear strength of the 1101 epoxy, but we got some really awesome, promising results that looked pretty darn strong, and we're excited for the future of that.
Yeah, so now we're starting off with some analysis. So we did FEA on our thrust plate. So the thrust plate takes the majority or all of the load from the motor, so it has to be strong enough to transfer all that load into the airframe. So we did a static study on the force from the M3400 motor, which is max thrust is around 4,000 newtons. From these results, we were able to further decrease the thickness of the bottom ring there from 1/4 inch to 0.15 inches. So just saving a little weight. A lot of that increase comes from the addition of the fillet around the outside there. Last year that was a big stress concentration, and now we can distribute that load around that fillet, so we can take off material elsewhere. This is just continuing through some of that FEA. You can see some of the factor safety in the top and the bottom. In the worst case, it's 4.68, so we have pretty good confidence that this component will be strong enough to withstand the loads. We also did some hand calculation on the height of the wall, just using the epoxy shear calculations from last year. We haven't actually plugged in the new numbers that we got from our lab shear testing, but we're looking to do that in the future, and that just informed our wall heights. So we're looking into that further. We also did a dynamic study just to see if there's any transient effects that are missed by the static study. It showed relatively similar results. We actually got a higher factor of safety of 6.12 using this setup, just making sure we don't miss any glaring issues during loading of this component, making sure it'll be strong enough.
Quick question, why do you think you got a higher factor of safety on the dynamic?
I can speak to that. I think it could have to do with the computation power, and just running a dynamic study takes a lot more power to get it to go. I think the mesh had to be slightly reduced, so it didn't take basically a day to run. So I think that the static's probably the better results. The dynamic, just to confirm that in a dynamic loading, we weren't going to see a crazy spike or have some time result that would cause a weird effect. So the statics are better test, and the dynamic confirms that nothing's happening over time.
Kay's been doing most of that work, so he's probably the point of contact if you have further questions about that. But hit the nail on the head.
Nice. Sorry, one more question. Any plans to make it thinner or try and shoot for a lower safety factor? Are you happy with the slightly oversized one?
I think we kind of like where we're at with the analysis now. A lot of we've heard, don't overanalyze your design, because then you start eating into your time that you can use for testing and for actual manufacturing. So I think for now we're gonna hold off. Maybe just looking at the wall height from the new lab shear testing, but for the thickness of that ring, it's probably pretty set by now.
Okay, sounds good. Thanks.
One more thing on that, the fillet is limited by the CNC and the actual ball mill tool head. So that's a little oversized, but there's no way to make that any smaller. So that's also why it's a little bigger.
Yeah, just because of the tools that are available to us.
Oh, sorry. I had a comment on the thrust plate FEA as well, actually. I just wanted to say that I think if you're seeing, you briefly mentioned that with a finer resolution mesh on the static case, you had a lower factor of safety, which means that you saw higher stress. Ideally, I know obviously you don't have all the computational power in the world, but I think what you should be trying to see is that the stress, the maximum von Mises stress should be independent of the mesh. So what you typically see as you increase the mesh refinement on and on, you'll see increasingly higher levels of von Mises equivalent stress. And eventually, what you want to see is that that level's off after you keep refining the mesh. So what tells me, what that's telling you when you're saying that the dynamic, which was done at a lower refinement, had, pretty significantly lower stress, that's telling me that your stress concentration is not totally independent of the mesh refinement yet. So I mean, I know, yeah, like I said, you don't have all the computational power you might want, but it would be worth at least going back into the static case and trying to see that what mesh resolution do I need to make sure that this is actually independent of the mesh, the stress concentration you're getting.
Yeah, that's a great point. I think we'll look into doing some mesh analysis. It's something we haven't really done in the past, so I think that's a good point. Thank you, Nick. Yeah, and then some more analysis we did on the payload structure FEA. So as you saw, and you will, as you saw in the CAD, and Ari will talk a little bit more about this. The payload is very integrated into the load path from recovery. So the U-bolt is actually directly attached to the payload. So all of the load from the parachutes is going into the payload structure. So we have to do some analysis to make sure that structure is strong enough to withstand those loads. So we did FEA on the top and bottom plates of the payload structure, and from these we were able to get a factor of safety of around 11 for both. So this further gives us confidence that this structure will be able to withstand those loads.
And just a note on that, I'm pretty sure Ari will mention later probably that he wants to reduce some of the mass in the payload, so this might be a good area to reduce some mass given that the factor of safety is around 11.5 right now.
Okay. I guess that's actually disappeared, but this is our payload bulkhead. This is the bulkhead that directly attached the payload. So those nubs you see on the bottom there, the payload slots up into those, and then you screw in. So this was a big point of analysis, making sure all those loads from parachute deployment actually are able to be withstood by this bulkhead. Matthew, do you remember what the factor of safety you got on this was?
I don't think we were confident that it was much higher than 1.5, but I'm not sure.
Yeah, it was. I know it was higher than 1.5. If you're curious of the actual number, you can send me a message and I can get that to you.
1.7 is the approximate calculated factor of safety. It experiences 230 newtons of load down through those nubs, and it's supported by those threaded rods. And yeah, 1.7 factor safety. That's the text info that should be out there.
So we actually did two simulations, one just for like the parachute loads, and then another for the loads experienced by the acceleration of the whole payload. So we have like a 4.4 pound payload being accelerated at like, what's the max acceleration? 14 G's. So from that you can calculate a force, and you can feed that force into the simulation. And from I think the overall was 1.7. Yeah.
Okay, and then for some of our analysis on just like the bolts specifically, we have tensile and shear bolt load calculators. So this is actually made by Nick. This is the inputs it takes are the design load and the external and internal thread geometry, and then the equations it uses are external and internal thread shear area, which is the really long equation on the right side, and then failure load formulas under tensile stress, and then use that to inform like any bolts that are under tensile stress, but mostly this is really important for the steel threaded rods that run through the av bay. And last year we had this problem where they only supplied quarter 20 threaded rods. So we weren't really able to optimize that too much, but this year Master seems to have accumulated a couple more sizes, so we're able to slim down to 1032 stainless steel threaded rods for an individual factor of safety of 2.19, overall of 4.38. And I wanted to keep the individual around like 1.5 to 2 rather than the overall, just in case. And the design load for that was 572 pounds. And then this is the calculator setup for the shear bolt load. Just uses the shear stress equation, and it takes in a couple geometry constraints for the bolts and material information. And this year we wanted to confirm that the shear bolt calculator actually works and is accurate. So we did a test of an instron test with 2 pieces of G10, and they were held together by a bolt. One was tapped and one had a clearance hole. And as you can see in that image right there, we had a perfect textbook case of it failing under shear. And we reached about 3.24 kilonewtons, which is on average across our 3 different samples. And that about lined up with our calculator. Our calculator said that it would fail at a bit of a lower load than that, but still around 3,000 newtons. So the takeaway is that the shear bolt load calculator agrees with the failure load seen in testing, which was very exciting.
This is some analysis we did on the bulkhead, specifically optimization. So last year we fed our bulkhead into Altair's topology optimization tool. So this year we did a similar thing with the aft airframe bulkhead. We used the results of the optimization to kind of inform the design. So if you saw the design earlier, that kind of like webbed pattern, those pockets there were mostly for weight saving. And that was able to get us a factor of safety of around 13.8.
Now we're going to go into the manufacturing plans. The fin assembly, it's going to be pretty standard to what we've done before, but we'll be cutting the body tube to size. And we will, this slide is actually not accurate. We designed the fins such that they would be able to fit in the water jet, which is very exciting. So this year we'll just be water jetting the carbon fiber fins. And then finishing the edges with file, sandpaper, or whatnot as needed, but the water jet should be pretty precise and get us exactly where we want to be much faster than our previous fabrication methods did. The aluminum fin mounts will also be water jet. And like we said before, we're just gonna attach those fin mounts through the wall and using 1101 epoxy. We're going to put the booster in the hot box that we made at about 86 degrees Fahrenheit. That's about as hot as we've been able to get it right now. And we'll just let that sit for a while. And finally, we'll just be able to put those fins into those fin mounts and attach it using bolts.
What kind of carbon fiber sheets are you getting for the fins?
5 32 of an inch quasi-isotropic carbon fiber is the plan.
From where?
Dragon plate.
Dragon plate. Okay, great.
For most of our aluminum components, especially the round ones, we will probably be CNCing them. So the timeline for that is to develop and execute a CNC program. And then for the thrust plate specifically, manually lathing the grooves for better epoxy adhesion, and then drill and tap. And yeah, for that we'll use the CNC mill, lathe, drill press, and taps. And then for the bulkheads, this would include the Avionics bay, aft, nose cone, and payload bulkheads. Those will also be CNC'd, and then drilled mounting holes and rail button holes, and tap those as well. So that'll reduce the metalworking fabrication timeline by a lot using the CNC wherever we can.
Sorry, real quick question on 2 slides ago in the thrust plate manufacturing. Are there any major changes from last year, or is it kind of the same thing?
Kind of the same thing, except the inner fillet on the inner edge of that wall, which would be the ball end mill or that other tool that you told me about recently that adds a fillet.
The bullnose end mill. I looked in there like $20 to $30 on McMaster, depending on the radius of corner you want. So
It seems
might be
to
an
have
option.
acquired some ball end mills this year, so we might
Oh.
rely on those, or we can look into the bullnose ones.
Oh yeah, I mean if there's already bull, you can always go with that. Yeah, nice.
Because we have so many like cylindrical components that we're CNCing this year, I might look into making CNC fixtures for those as well, just to hold them down better, because last year we just used like hemispherical kind of clamps, and those were okay, but it would get an uneven finish on the bottom side when you finished facing it off. So that might be a good area to make some pictures for the CNC.
Yeah, for sure. Yeah, nice.
The removal fin mounts, their fabrication is gonna be pretty simple. It's just gonna be that 7075 aluminum, and we're just gonna water jet and then mill it down as we need to. Our current biggest open issue is just making sure that those fin mounts will be able to prevent any deflection of the removable fins. We don't want any wobbling or what have you.
The avionics bay is a bit involved and all over the place, but basically fabricate bulkheads using CNC, cut the avionics bay tube to size, drill and tap mounting holes, and then install the threaded rods, laser cut the sled, and then mount the sled using any brackets, and then finally install the electronics hardware. So those will be using CNC mill, Dremel, sandpaper, water jet, laser cutter, and 3D printer. And only open issue with that so far is just how we're going to implement wire management into that.
Went over this with the fin assembly, but the fins, we're just gonna cut down the stock so it fits in the water jet it, and then finish as needed. You can kind of see how we manufactured Hodge's fins last year. Those were too big to fit in the water jet, so those were hand dremeled and then filed down to size, which took a good 2 hours, I'd say.
For the camera mounts, these are just gonna be the 3D printed, and then we're gonna install some heat set inserts, install the hardware, the cameras, the PCBs, and assemble it, and then bolt it into the airframe. So mostly just 3D printed.
So as soon as we get back from winter break, we're gonna start building the rocket. We're gonna try and order, an issue we ran into last year was that we weren't able to order the parts, the stock that we needed until we got back from winter break. So we spent a lot of time in January just waiting for those to come in. So we're gonna try and do a first order at the very start of winter break and then order more as soon as we get back. So that way we'll be able to hit the ground running when we get back to campus in January. Mechanical fabrication is super important because a lot of the other systems rely on it, and we need to do a bunch of testing with it before we can fly. So we'll be in a lot of communication with the other teams. So in the aft end of the rocket, we're going to start with the fin assembly and motor mount, and then we'll work on the fins. And at the same time, we're going to start machining the thrust plate and the bulkheads. And lastly, the avionics bay will come together, so will the stop rings.
And we're also, right when we get back, gonna try to get the entirety of the air brake structure done so that electronics can start like working on getting that integrated and testing. This is just our risk matrix. The entries correspond to the rankings of how likely we think they'll occur and then how they affect the mission. For the high risk happenings, the first one is the thrust plate detaches from the airframe after the boost phase or during parachute deployment. Our risk reduction plan for this would be to test the strength of 1101 epoxy with lap shear tests, which we already did, run simulations to optimize while maintaining a proper proper factor of safety and ensure proper bond prep when constructing. Second entry is structural failure of air brakes. This would be addressed in material choice, attempting to retract them before landing so that they don't get damaged upon impact with the ground. FEA unexpected loads, and then physical load tests / like ground or flight testing, just to ensure that they can work well and not get damaged during the flight. And then the ab bay closure can also fail, which would result in electronics damage. And for this, to address this, we would make sure the all threads are thick enough to handle the flight loads, make sure that the coupler tube is epoxied properly, and then double check tightening of locking wing nuts during integration. If the payload attachment fails, we can make sure that we reduce this risk by performing hand calculations or FEA analysis on the connection points and U-bolt on the bottom face of the payload. Also selecting the U-bolt to ensure that it's rated for the load that the payload is going to be taking. And then airframe separation failure, we can ensure tight tolerances between sections with smooth connecting surfaces, but tight tolerances meaning that they're not so tight that it can't actually separate.
As for our mid-range risks, the first one is potential mechanical failure of bulkheads. So that one we're mostly just going to mitigate by using FEA to make sure that the bulkhead is thick enough to withstand all the loads it's going to face. Next would be that the fin mounts themselves break or deform. So again, that's FEA, and then just working to make sure that it's not hitting the ground super hard. Next would be the rocket landing outside of acceptable landing speed. So essentially making sure that everything is like adequately reinforced to endure the impact, and that the fin geometry is designed so that way the load will be minimized if there is an overly fast impact. The rail button brakes, we're gonna use a metal rail button and manufacture ourselves to try and make it stronger. We're gonna try to stop the parachute from tearing by just making sure that all threads don't protrude too much, and keeping pretty low profile on wing nuts and other components. That way there's less of a chance of like snagging or tearing on the parachute as it deploys. And then finally, Izzy kind of touched on this, but the potential for mechanical failure of U-bolts. We'll be doing FEA analysis and calculations and otherwise just working to make sure that the U-bolts can endure the load that they're going to face during flight.
And then finally for our more risks, the nozzle could break due to a lack of support. So we will fabricate a support to act as a rail button stop, and be careful about the setup. If the fin breaks or deforms on landing, we will have backup fins in case it breaks, and we will try to soften the landing and do some FEA air console to feed in our analysis to make sure nothing happens. The rail button attachment could fail, so to mitigate that, we will connect rail buttons to hard points. As you saw, the nubs on a lot of the bulkheads, those should act as hard points, and we can use FEA to make sure none of those components will break. Our cameras could fail if they become hot so we will make sure the camera connections can handle ascent conditions, that the camera is turned on and with adequate battery life. We can have mechanical failure of stop rings, so we will use our lap shear test to size the stop rings, make sure that those calculations are enough to handle the loads we expect from deployment and from other loading conditions. And our last risk is that the air brakes do not deploy. This won't be a horrible issue because we just won't be able to reduce our apogee. But to mitigate this, we will perform comprehensive analysis of the system using FEA ground testing and using our test flights to make sure at the composition they work as intended. One thing about the air brake, sorry, Nico, I forgot to answer your question when talking about this, but we made a simulating study or a simulation. Our drag numbers for our air brakes are very much still up in question. That's an open issue that we are working on. But for our simulating study, the drag was basically just a flat plate in flow. So that was like the drag coefficient, and using the maximum deflection area, we could calculate a drag number. And then I just, in the simulation, I just applied that increased drag at the earliest possible deployment. So assuming the air brakes deploy to 100% at the earliest time, I found that the altitude decreased about 1,000 feet. So that was the number we were designing around and sizing our motor based off.
Nice, good to know.
And then some open issues we have remaining to be addressed are just designing fixtures for CNC machining, like I mentioned, wire management for the avionics bay, calculations of Poisson's ratio and maximum shear stress using the lap shear test data, and then finalizing camera mount design and perform analysis just to make sure like they're not overheating or that they can handle the flight loads without too much drag as well, since they're protruding from the avionics bay. And then O-ring calculations for aft airframe bulkhead and air brake flow analysis to get a drag force equation and inform simulations.
Finally, our schedules to completion. Airframe, we're going to try and get it done about a month, give or take, from returning to campus, but it's just going to be a lot of cutting tubes, cutting fins, and epoxying things together.
And then for metal, complete optimization of bulkheads and using the lap shear test to validate the thrust plate wall height. That'll be completed over winter break just so we can hit the ground running fabrication when we get back. And then the thrust plate and air brakes is not listed on here, but also should be done very early on in January. And then also the fin mounts, and then fabricating all bulkheads will follow and hopefully be done by February 11th. So.
That's all we have for mechanicals. Do you all have any questions about anything we covered?
If it's okay, I just wanted to say something more about the FEA since you're doing a lot of it. Especially, you know, as you mentioned before, especially for the dynamic simulation, that was a lot more resource intensive. So you weren't able to use as nice of a mesh as possible. Something that you can do that you should kind of look into, especially because, you know, you're doing simulations of a lot of geometrically, I would say, simple parts like, you know, circles as your bulkheads. You should look about like what kind of planes of symmetry you can use to reduce the complexity of your simulation, right? So if you imagine like with your bulkhead part, it's basically a circle, right? If you take a sort of pie shaped slice about it, that's actually, you know, symmetric with the entire part. So a lot of times you can really reduce the computation time because, you know, suppose you have some part that is symmetrical across one plane. You can literally in the simulation just cut that in half and just study half of it, and that halves your mesh, right? So that allows you to, you know, get a lot higher resolution in your simulation. You just want to be careful about, you know, how you treat that half, like where it would in theory connect to the other half. But that's a really powerful trick you can use to save a lot of time.
We'll definitely look into that. Thanks.
Any other questions?
Yeah, for slide. Oh, also, great job everyone on getting to this point already. No, it's a lot of work and a lot of like optimization and effort to get everything to here. So very good job, very good job. I had a question on the plan for the air brakes. So seems like a great idea to retract them before landing so they don't get damaged. Have you guys thought at all about retracting them either right before apogee or at apogee to try and reduce the chance of tangling, like during drogue deploy?
I think the plan is to retract them like right at apogee or after apogee, like as you said, in that range. I think, I don't know, Avionics, you could go into a little more detail on like the states.
We go to the states, but we haven't gotten into when we could retract them. I think apogee would be a good place for that. It's a good idea.
But it's definitely something we will look into. But yes.
Nice.
With the drogue deployment would be a major concern with the air brakes because of the positioning in relation to the drogue deployment, because the drogue is deploying right under the nose cone and the air brakes are at the top of the there's like a lot of room for, like, I don't know that they're going to interact.
I think it's best to just reduce the possibility of that, like, because I guess once the rocket hits apogee, like it's kind of pointed down, so even if it really is at the nose cone, the shroud lines could like run along the length of the airframe, which could tangle with the air brakes if they're deployed. So I think just now wherever possible.
I think it's also worth noting that the rules and requirements actually say that any active controls such as air brakes need to default to a neutral state in a loss of power. So I think adding on the ability just to have them immediately retract at apogee and return to that neutral default state would be good. And it would pair nicely with returning to that closed state anyways in a power loss.
Nice. Yeah, the only situation which I can think of where it would be good to have the air brakes out after apogee would be if you don't get the drogue out, and then you want it to like slow down. But that might be a more of a contingency plan.
Yeah, I don't think that would be technically allowed within the rules of the DTEC because they have like very specific requirements for active control surfaces. Like we can't exceed a strict like angle of attack, or it can't be before maximum dynamic pressure or 6,000 feet. So I think it technically can only be used during like the upward phase, but yeah.
Nice. Okay, one more question on air brakes. You guys said you were going to do some more analysis simulations on the air brakes. Is that going to include anything about how the air brakes and fins interact? Were there any plans to like try and at least mitigate that?
We've met with Erica, and she's kind of been trying to inform our like aero decisions around the air brakes. But kind of the consensus there was that it's very difficult to model the effects in that large of a range. And we've been kind of working to make a simulation, but we've run into a lot of issues. So what we've done to mitigate those effects are the air brakes are just offset from the position of the fins.
Nice.
And we did make them, like we moved the air brakes aft, so they're closer to the fins. So hopefully any vortexes or anything like that doesn't have the time to develop adequately to put some weird forces on the fins. But that's something we will have to see during our test flights mostly.
Yeah, the air
Sounds
brakes
good.
are 45 degrees off the fins, so hopefully they won't interact too much. And then we're currently starting a big like literature review for experimental data like that people have found of flat plates in flow to kind of use that as our stand-in for a simulation of air brakes, because it's very hard to actually simulate it with. So we'll be relying on hopefully finding experimental data that fits our situation.
Nice. Yeah, the clocking should help a lot. Yeah, only asking because like the flat plates should have a decently large wake, and if that's like spreads out too much or isn't too well attached to the airframe, then it could get in the fins. But yeah, that sounds good. Okay, last couple questions from me, and then I'll leave you guys to it. I think there's more info on this in the recovery section, but just remind me, what were the loads for the drogue deployment and parachute deployment that you guys used for your analysis?
I want to say 370 pounds off the top of my 380 pounds off the top of my head. I don't know if that's changed, but
There were a couple different ones depending on, I think there were like 4 different ones. The lower ended ones were like 48-ish, and then the higher ones were like around 270 and 380.
Okay, yeah, I see 380 on bulkheads. I saw 570 on bolts as the
Yeah.
design load?
That was just like the factor of safety multiplied by the
Okay. Nice. And then on main parachute deployment load, do you remember what it was?
Min is 89, 88, and then max is 500.
and if you're
Sorry,
saying
main, not min.
if you're seeing like weird numbers that don't seem to match with those, we also decided between what was a higher number of, if it experienced a higher number under acceleration, some of the analysis was conducted using that number, or if it was higher for the shock load, then that was the number that was used.
So that was
Nice. Yeah. Sorry, go ahead.
the main expected was 88.
Pounds?
Yeah.
What's 88 pounds in newtons?
Working eagles here.
88 pounds is 390 newtons, right? Okay. Okay, sounds good. Yeah, I just want to make sure that the stuff on the main is, or at least the there's a good understanding of where the loads come from in the first place, because you can have a very, very well set up simulation and calculations, and if the original requirements are a little bit out, then that could present some risk. But I think that should be good.
Any other questions?
Okay, we're gonna run into payload.
Thank you, everyone.
Everyone. I'm going to present on the payload for this year. So, my name is Ari. I'm a junior. I'm a political science major. So the purpose of this year's payload is to test the change in efficiency of solar cells at various altitudes recorded during descent. It is going to be oriented in such a way that the CubeSat form factor will be exposed to light upon drogue separation at apogee, allowing these solar cells to produce energy as the rocket descends. And we'll be conducting ground testing throughout next semester to gain a better understanding of solar cell efficiency in a controlled environment, the effect of indirect sunlight at various angles on produced energy, and how the received light is reduced due to the parachute shadow on descent. You can see a little graph there that is air density and altitude, just to sort of get a sense of how the atmosphere thickens as you get lower and closer to the ground. So design overview, it will be 2U, which is 10 centimeters by 10 centimeters by 20 centimeters, and it will go into 10,000 feet. And our goal is for it to weigh 4.4 pounds, and it needs to be easily accessible so that it can be weighed and measured at the competition. To test the change in efficiency of these solar panels during descent, we are going to be collecting and analyzing the change in power/current output with an SRAD board that is being designed by the electrical subteam. The payload is going to be sitting in the forward airframe and is an attachment point between the nose cone and the drogue parachute. And the payload is secured to a bulkhead at the bottom of the nose cone, which is then secured by those all threads that were mentioned before to another bulkhead higher up in the nose cone. And it will be adhering to all the other competition-specific rules and requirements. So this is the whole nose cone and payload assembly, just so that you can get a sense of what it looks like when we're talking about it in more detail. So the bulkhead, as was sort of mentioned before by the mechanical team, is bolted to the top piece of the payload, which I'll mention in a little bit, is connected to the nose cone through all threads into another upper bulkhead. It connects the payload to the nose cone, and this is going to be something that's more of a mechanical team responsibility and less of a payload team responsibility, just for manufacturing and analysis. This is the actual structure of the payload. Just so you can see the 10 centimeters, 10 centimeters, 20 centimeters. It is going to be 2 kilograms / 4.4 pounds. It is going to be constructed of 6061 aluminum panels. Right now, it is over 5 pounds, which obviously is more than the 4.4 pounds we want it to be. So we have to reduce that, as was mentioned by the mechanical team. I'll go into a little bit more detail on that in a bit, but just it's one of our open issues. And then it houses the payload experiment, the solar panels on the sides, and the electronics inside. And I don't know how obvious it is to see, but if you look through that sort of front solar panel on the side. There's like a little green spot, and that is like the sled that I will go into more detail on in a second, but that's where the electronics will be sitting. So there are two types of sides to the payload. There is a long side and a short side, just for ease of assembly. So these are the long sides. There is a cutout for the solar panel, which is what is facing us in the image on the left. And there are bolts from that to the short sides, which are those 4 holes on the face. And then there are also bolts from the top and bottom pieces, which are the ones shockingly on the top and the bottom. And then there is a slot for the electronic sled, which is that little groove that you can see running through the image on the right. These are the short sides, very similar to the long sides. They have cut out for the solar panel, and they have bolts from the long sides, and those are on the sides of these faces instead of being on the front. And then there are also the bolts from the top and bottom. There is no groove for this electronic sled here because of just the way it's oriented. We only need one, so we just put them on the other long sides instead of the short sides. This is the electronic sled. As you can see, it's a really detailed image. So it's going to be sliding into those grooves along the long side of the payload. It's going to be probably made of birch. The board, the SRAD board, and the battery will be sitting on here, and it will be attached to the bottom face for easy assembly and removal. And then there will be little cutouts. We just haven't decided where yet on the board, so that way we can get wires from the solar panels that are on the opposite side of the electronic sled from the SRAD board through to the SRAD board. This is the top piece. It is attached to the payload bulkhead. It is bolted into all 4 of the side pieces, and it keeps the electronic sled from any horizontal or vertical movement through the slit that is right across the bottom there. And this is the bottom piece of the payload. The 2 middle holes are the attachment points for the U-bolt that will be connected to the drogue parachute. And then the 4 holes along the outside are where it will bolt into the 4 side pieces of the payload. And it will be attached to the electronic sled so that we can easily remove it without having to take apart the entire payload. And this is just sort of like a stand-in for the solar panels. It's a solar panel. We are not making them. They are COTS. We're buying them. It is attached to the 4 side pieces. At this time, we aren't really sure how we're going to attach them yet. We have to do some ground testing and flight testing on that one just to check. So I don't want to give any definite statements on the attachment method.
Yeah, the commercial off-the-shelf payload solar panels are already sourced. We have them in our makerspace, and they come with commercial gaskets. But I guess the primary thing is that we want to test how strong those gaskets seal the solar panel to the payload itself, and how robust they will be. So that's some of that open issue testing.
Yeah, and I'll come back to that on a later slide just to reiterate that. But yeah, thank you. And then they will be wired to the SRAD board inside. I probably should have put a picture of the solar panels now that I actually think about it, rather than just having this. But basically, there are 2 connection points on the back of the solar panels that will just be able to put wires there and attach that to the SRAD board. So analysis, because I'm not the mechanical engineer, the analysis is being done by the mechanical team, because frankly, as much as I try to understand, I'm not, an expert at that. But they are working very closely with us on that. And we need to optimize the payload itself to determine how much mass can be reduced. Obviously, we need to reduce minimum like 0.6 pounds. And so that is something that the mechanical team is looking into to determine how we can get rid of that weight without compromising structural integrity. And then We also need to double check all the shear and tensile strength calculations for the bolts used between all the individual parts of the payload and the payload bulkhead. Our manufacturing plan for the sides, top and bottom, so just like the entire structure of the payload, is that it's gonna be made out of aluminum 6061. There are 6 parts to it. Yeah, 6. And the current idea is to mill the parts to size and then cut out the space in the side pieces with the mill also. There's an open question on whether or not we might be able to use CNC for that. That is something that is still to be discussed. We haven't really gotten into great detail on that yet, but it's just something we're considering to try and get those cutouts for the solar panels to be as square as possible. And then the holes in the pieces will all be made using the mill, and just as we've done in past last year, just putting them on there, just milling out the holes. The electronic sled, right now we're planning on it being laser cut birch. It can be laser cut because it has no load and it's not have any forces running through it that could really break it. So it's not important that it really be that robust of a piece, and that is somewhere that then we can cut down on weight by not having it be a thicker piece or made of a heavier material. And then the bulkhead will be made by the mechanical team with the CNC. Again, that's not something that we're really focusing on, given that that is much more of a structural issue for the rest of the rocket. So the integration plan for the payload, or rough integration plan, I should say, that will probably change as we actually go through the process of making it and then testing it, is that the solar panels will be mounted to the side pieces, and then the top and side pieces will be assembled and bolted together. And we will then slide the electronic sled into the payload, which is obviously attached to that bottom piece, so that will then be bolted into the sides. We will then take the whole thing and bolt the top piece into the bulkhead, and then we will attach the drogue parachute to the U-bolt on the bottom of the base. And the beauty of this payload is that it can be removed and resecured at any time it's needed. It's very easy to take apart, and it's very easy to reassemble. This is our risk matrix. As you can see, there are a couple of bigger risks and a couple of things that are really not things that we're really concerned about. So our first major risk is that the payload separates from the bulkhead. This would obviously result in the loss of the nose cone, and that would be very bad for the rocket. We are going to reduce this risk by, we have done and will redo shear calculations on the bolts, and then we're just going to make sure that we test it during flight, and we will also ensure that we are properly assembling it and securing it. Our next big issue is it's sort of 3 separate issues, but they all are the same concept, which is that any of the individual pieces were to break off from the payload, this probably would result in, again, loss of the nose cone and loss of the payload. So we're using the same sort of risk reduction plan of just redoing and checking our tensile and shear strength calculations on any bolts or mechanical fasteners we're using, and then just ensuring that we assemble it well and securely when we are going to fly. Our third issue that is that you can see is going to have less of an impact, but it's a little more likely at this time, is that the solar panels themselves actually detach from the payload. We're going to try and do ground and flight testing on the attachment method, and then ensure that it is properly secured during integration. Right now, I'm saying it's a little more likely to happen just because we haven't done that testing yet. So we don't really have a great sense of attachment method and how well that attachment method will work. But we're hopeful that that risk will then come down dramatically once we've done that testing. Next major risk is that the U-bolt on the bottom face fails. If that happens, obviously, once again, we lose the nose cone. However, given our many years of experience now with U-bolts and with recovery operations, and given all the simulation work that's been done, I don't think it's that high a risk of it happening. But just to ensure that it doesn't, we're going to do FEA calculations to ensure that it is that the bomb face and the U-bolt have a proper factor of safety for the expected shock load, and ensure that we choose a U-bolt that can handle that shock load. And now for our less serious and less likely issues, if these solar panels are damaged by ejection charges, that would result in us possibly losing the experiment. However, it would not damage the rocket as a whole or our chances of recovering the rocket safely. But we are going to do ground testing and flight testing to ensure that we can plan for this and try and reduce the risk as necessary and adjust our design based on the outcome of those tests. And then our last two risks are that the wiring between the solar panels and the SRAD board fail. Again, if this happens, we will possibly lose the experiment, possibly not gather the data we want to gather. However, it would not impact our recovery or the rocket as a whole. Basically, just we're going to make sure that it's built well, we solder the connections well, and then it will be tested on test flight 2 definitely, and maybe on test flight 1 if it's ready in time. And based on that, we will adjust design if we need to rebuild it, if there are any issues that we notice. And then our last one is that the internal SRAD board fails. Again, same thing as the last two. If this happens, we will probably lose the experiment. However, it would not affect the rocket as a whole. To ensure that this doesn't happen, we're going to perform testing to ensure that the board is functioning properly. We're going to ensure that the batteries that we're using can provide consistent power to it for a long period of time. And then again, we will hopefully have this ready for test flight 1 and definitely have it ready for test flight 2. We'll be able to get a sense of how it functions on the actual flight. So, few open issues. We have to optimize the design for mass, just to make sure that we are not going to be up to a pound overweight. We have to still complete the SRAD computer design that is not yet finished. We need to test the attachment methods for the solar panels. So as Ben mentioned before, they came with gaskets when we bought them. We have no idea if they will be remotely sufficient for actually using them in flight. So we're going to do a combination of ground testing, but also flight testing just to see if they will work. And if they do, that will obviously be our best solution. And if they don't, we have to then figure out a different attachment method that will not damage the boards or the solar panels. Sorry. Last thing, we have to test if the ejection charge deployment damages the solar panels. We are going to mostly test this through ejection testing here on the ground, but also we will hopefully get to test that in flight on test flight 1 or test flight 2. And then we will be able to adjust our design accordingly and make any changes that we need to make. Schedule to completion is not nearly as nice as the mechanical slides, so I apologize for that. But in January, we're going to begin manufacturing and finish the board design. And then also in January and early February, we're going to test solar panel attachment methods here on the ground and maybe also in flight. In early February, so before test flight 1, we are going to finish manufacturing the structure. So that way on test flight 1, we are able to definitely fly the non-functional payload, just the structure. And hopefully we will fly at least one solar panel because we have extra ones that we bought to ensure that the result of ground testings of our attachment method are correct and actually hold up in the real world. And if we have the electronics ready in time, we would like to fly them on test flight 1 and fly the fully functional payload, but that's sort of like a best case scenario, really like hope for that, but there's no pressure to ensure that is done in time for test flight 1. Then in March, we're going to do more ground testing of the electronics of the solar panels if we don't fly them on test flight 1 and have yet to really gather much data in experiments. And then April, we will fly the fully functional payload on test flight 2. And then in June, fly at IREC and collect and analyze the data, and hope maybe like win an award for it. That would be kind of cool. So yeah, that's all. If there's any questions, happy to take them / direct them to the right person. Otherwise, recovery.
Yeah, I got a question.
Yeah, what's up?
Maybe I missed it earlier in the talk, but what data specifically are you collecting?
I can take that.
So we're measuring the current draw from each panel. And then
Okay.
we also have a barometer on there that's measuring the altitude, so we can keep track of it as a function of that.
Okay. I would suggest at the very least, throwing in an IMU, maybe a 6-axis plus magnometer or 9-axis, because you could measure the current current as a function of altitude, but there's definitely a bunch of other stuff that's coming into play there, such as whether or not the panel is actually facing the sun, which I guess you could maybe figure that out, like what angle what the sun rays are, hitting the solar panels at given the specific time of day. But I just wanted to put it out there that it's not going to be directly. There's more factors coming into play with the efficiency of the solar panels than just air density.
Yeah, in terms of like angle that the solar panels are at, we actually did consider this pretty early on. And one thing we realized is that it's going to be spinning and moving so fast that the IMU probably would not be able to keep up with the data collection and would not be able to really get a great trend between orientation and the data we collect from the solar panels. Electrical, you're welcome to go into a little more technical detail on that, but that's just sort of the overview of what we've thought of.
Yeah, I think it also wouldn't take that much effort to add it on if we just in case. So I think we could add it.
I think so. We had talked with a professor about this, and we also mentioned that because the recovery or the payload is attached to the recovery device via swivel link, it's going to rotate so quickly that just averaging out, like if you get the IMU data, like yeah, you can see like where it will position relative to the sun, but it's going to be revolving like several times per second. So like you're just going to look at an average trend, and all the 4 sides are like on an average going to be facing the sun at the same time. So that I don't think that data is really going to help us with our like conclusion at all.
But as Catherine said, with not much effort, we might as well throw it on just to see.
If I might throw in a word of support for Daniel here. Yeah, it all depends on the frequency, on 2 things actually. The frequency that you can get data from the accelerometers and the frequency that the is able to read and save the voltage coming from the solar panels. I will say from my experience working on rocket parts that spin at very many thousands of times per minute, there are ways to do it. I'm not necessarily all familiar with those ways, but yeah, if it's spinning to the point where it's beyond the frequency of the data that you're able to collect on both the voltage and the acceleration, then yeah, it'll be something average, but it'll be average between the light side and the non-directly lit side. But if you're somehow able to get high enough frequency acceleration data, which at four times per second spinning of the payload would mean if you get 40 hertz acceleration data and voltage data, then you'll have at least a very rudimentary baseline of sort of what the voltage is on each side. And if I remember correctly, we had something like 20 hertz last year. So even then you should be able to see some difference, and you can pick sections of the data based, or sort the data points based on the angle and incident angle of the sun. And if you get the 9 degrees of freedom stuff, you could do absolute position facing the sun and do lots of cool math there. But yeah, hopefully it shouldn't be too hard to get that kind of frequency, sort of in the 40 to 60 hertz range of data. But if that's an option, I definitely support Daniel in going for that.
We'll definitely keep discussing it, thinking about it, but we definitely appreciate the idea and the comment.
Of course.
Yeah,
Yeah,
just
only
to-
if you guys get around to it. Sorry, Daniel, go ahead.
No, you're cool. I just want to double down and say that you know, I think I'm assuming that what you would be doing is just connecting the sensors via I2C, correct? Right?
Yeah, I'm getting nods.
Okay, cool. So you could get higher frequency, higher sampling rates if instead you connect them all via SP. Well, I don't know what you're using your SPI pins for, but if you can connect both the barometer and the IMU via SPI and instead use the FIFO buffer to just collect I'm assuming it should have, they should both have FIFO buffers, but if you use that to do data collection en masse instead of continuous polling, you should be able to get pretty good granularity of, each delta T.
Sounds great. I'll be honest, I'm not entirely sure what you just said, but it seems like the people who understand it we're following along.
Yeah, that was mostly for electrical.
We'll keep that in mind.
Yeah. If there's nothing else.
Sorry, I do have another question.
Oh no, I'm always happy to hear your voice, Nico.
Thanks, sorry. Okay. Let's see if I wrote down the slide on this. For the payload structure, FEA, sorry, I know this is back in the mechanical section, but this is slide 52, if you'd mind going back to that. Also, I love the solar panel idea. I think that's super cool. I'm very excited to see what the data looks like.
Shout out to Ben. That was his idea.
So yeah, question was, where's the 48-pound deployment load from?
Oh, that's from the rogue average, I believe, that we anticipate.
What do you mean drogue average?
What's that mean?
What does that mean? It was before we adjusted it.
Wait.
Before we swap
Yeah.
AR.
Yeah. Is that?
Oh.
Because if
Yeah.
that's the main load, yeah.
Okay, we'll have to address that over the break.
I think we might have.
Yeah.
Have you looked at this one?
No.
I think the 48 is the updated, and you guys have the updated.
You have updated?
Wait. Can I just say, so from in the recovery section, I'm seeing on main expected 88.5 pounds, max 547.6 pounds, both from PIFCalc, and then on drogue expected 79.4 pounds, max 256 pounds. And then just wanted make sure I'm understanding this right. The drogue is the one right below the payload now?
Yes.
Okay. Yeah, so I'd expect that load to be, 79.4 if you're going with that, but 256 on pounds on the max. Right?
256.
So let me just.
Yeah, sorry for the confusion. I just want to.
It's a good thing.
So the 256 is the drogue, but it's split among the payload structure and the avionics bay. And due to the chute length, due to the recovery harness lengths, the majority of that 256 load is on the avionics bay U-bolt, and it's only whatever it is, 48. It's only the 48 that's on the payload recovery side.
Okay, so the 48-pound load is, you got it by running OSCalc or PIFCalc with the nose cone section as a placeholder for the rocket?
Yeah, it's I forgot which OSCalc or PIFCalc, but it's PIFCalc on the specific section. Yeah.
It was just a matter of mass.
Okay. Interesting. Yeah, no, I wanted to make sure on this one, and then especially on the payload bulkhead, that the loads there aren't just somehow undercooked. Because like the first, yeah, okay, um, that
Sorry,
makes sense conceptually. I think.
It's not properly reflected in the slide, but basically that maximum PIF calc main 547 and then maximum PIF calc drogue 256 is the load itself as a whole, and then it's split within each of the connection points. So the nose cone takes a lot less of the drogue load than the avionics bay, and same thing with the main.
Doesn't that assume both lines go taut at the same time?
So no, because the if calc uses the wait, I need to double check the math, but the reef time I think is the time that the wait, no, PIF calc doesn't take reef time. No, it does.
Like fill time?
Yeah.
And OSCalc does. I always forget the difference between
No,
the two.
it's the opposite. OSCalc doesn't take fill time. PIF calc does. We used the same fill time for both. They would go taut at a different time, but the parachute would. I don't know, that would be a negligible difference.
Sorry, I know it's always the chute deployment loads that are up in the air.
Wait, this is a recovery question, Nico.
Okay. No, the only reason I brought it up now is one for the payload structure, but mostly for the payload bulkhead back on slide, payload bulkhead FEA on slide 53. Because they had the 230 Newton load there, I just wanted to make sure that, because I know that one's coming from gravity or acceleration on ascent and weight of the payload. Just wanted to make sure that there wasn't like somehow a flip in the loads, because yeah, just for safety. If not, we can put it off to recovery loads. Happy to do that.
What you're saying?
Otherwise, payload. Sorry.
You're saying that the numbers didn't align.
No, I was saying for the analysis slide for payload bulkhead, at least the slides I see say 230 newtons here, which I assume is coming from the acceleration due to like the max acceleration on ascent. I just wanted to make sure that the drogue deploy load wasn't somehow higher, because if the drogue load is higher and your safety factor is already 1.7, then even just using the like 79.4 pounds from OSCalc, you already get a safety factor below 1, which is not ideal. So I just want to make sure that the loads are all set there.
Yeah, the 230 newtons on the payload bulkhead, I believe, is the same as the payload structure FEA. It becomes like 52-pound force, which compared to like the 48-pound force, it might be a miscommunication or a conversion error, but they are roughly the same force.
Oh, okay. And then if it's 14G max, or is it 13G max on acceleration?
13.9.
Okay, that's giving me 274 newtons.
Why are you taking the acceleration during ascent?
Because the payload weighs 14 times more, as it's like pulling 14 Gs on ascent. Or weighs 14 times more.
Wait, but you're discussing the load during
Yeah, the original question was load during deploy, because I thought the 230 was load during ascent.
Oh, you're right.
230.
So it's 270, you said?
I said I'm getting 274 from like
For the acceleration.
4.4 times 4. Yeah. Here, I can just text you.
Oh yeah, 32 times 4.4 times 14.
Yeah.
We don't have a calculator.
For a
Okay, yeah,
calculator, by the way.
that's something we'll look into. Thank you for
cool.
that.
All right, I'll try and think, and if I can wrap my head around the like other
Yeah, no,
the
I
split and the
think-
parachute loads.
I
and
think
the
we were under the impression that the deployment load would just be greater than the acceleration.
Yeah.
I think we actually had a pretty late motor switch up, which Ellen will talk about in propulsion, which is
Nice.
why we're focusing more on the deployment loads than the acceleration loads. But that's a very good point, and we will look into that.
Sounds good.
230 to 270 isn't like a huge jump, so we already have a pretty high factor of safety. But if things need to be readjusted, we will do that.
Any other payload questions?
Sorry, 1 second. Yeah. Okay, yeah. With the 270, you drop just below the 1.5, so it's should be easy to fix. Otherwise, payload looks good. Question for Ari real quick is, are there any, or sort of what kind of risks do you anticipate from the internals getting knocked around during either drogue deploy or main deploy or on landing? Or is there any thoughts around like saving data or protecting internal components and boards and whatnot?
I vaguely remember us discussing this at some point, and us saying that there isn't like a major risk of any kind. But if anyone from
Okay.
electrical like knows anything that I don't about this, you're wrong. I don't know what that was supposed to
The
represent.
slot. I mean, so when it comes to the actual like board and batteries themselves, they're all gonna be attached securely to the sled. And the sled, I guess we don't have a great visual of it. If you can go back to the
I see what you're saying.
Yeah. So the sled is designed to basically slide into those slots. Can you go to the other diagram on the sides? Yeah. So each of the surrounding aluminum machined payload sides has a slot that the sled will kind of fit into. So that was done to reduce vibrations on ascent and on recovery. So the idea is hopefully the board's going to be secured to the bottom side, and then each of these slots will keep the board itself from deflecting and vibrating, and hopefully from flow down that will be okay.
Got it. Okay, nice. And if anything comes loose or falls away, it'll stay inside the payload, right?
Yes. Yeah. It's more contained actually than last year's.
Oh, very good. Now, any plans on how to make those sides, or is that still in flux down the line?
What or like as a whole or like a specific aspect?
Just the long side there.
We'll originally just get stock and mill it down to size, and then for the holes in it, we'll use the mill and just mill those out. And for the cutout for the solar panels, right now we're planning on making that on the mill, though there was an idea mentioned to possibly see if we can do that with CNC, just to get the right angles to be as proper and as close to 90 degrees as possible, to ensure that it's as close to a perfect fit for the solar panels as possible. But that's something that Izzy and I have to discuss later. We haven't really gone into that particular aspect of it yet. And then for the groove, that hasn't really been considered yet, but probably also something that would be made on the mill or the CNC, but again, also something we do need to have a future discussion about, I think.
And yeah, if you want for the solar panel stuff, that like step cutout on the left side, if you keep the like middle sections of those flat things where they are, and then sort of like widen out the corners, it should be able to be a lot easier to make on the manual mill. Will still take a lot of time and be a lot of fun. But okay, nice. Yeah, great job. Payload's super exciting. Can't wait to see what it looks like.
Thank you.
So Juliana is feeling ill, so Ben and I are gonna take recovery. What the hell is it? So. So just IREC requirements for recovery to streamline, we need to have dual deployment with drogue at 10,000 feet and main under 1,500 feet, with drogue under 100 between 65 and 131 feet per second descent, and main under 36 feet per second. We're going to have SRAD flight computer as our primary energetic, and per requirements, COTS backup energetic. We need redundant energetics, and connecting the harnesses, preventing harnesses from being overly twisted, and then contrasting colors with the parachutes. We need video recording our ground tests of ground tests prior to flight, which we have every intention of doing. Wire management has to be controlled, safe handling of energetics.
So these are some of the interfaces that we need to consider when it comes to the recovery scheme. On the mechanical side, there's been a lot of talk about this, but it's all the connection points, all the bulkheads, the U-bolts, and the quick links. The main chute, of course, is stored within the aft airframe, and the drogue chute is, of course, stored within the forward airframe. Hopefully, we've covered the majority of those connection points on the mechanical payload slides, and how the chute loads are all affecting those factors of safety. On the avionics and electrical side, of course, you have the flight computers controlling ejections. You have the CO2 system inside the avionics bay. You need the current forward igniters, and you need that deploy signal. And then, like I just mentioned, payload adapters taking that load of the drogue ejection.
So concept of operation similar to systems. Rocket lifts off, motor burn out at around 1,700 feet. Then air brakes slowing into 10,000 feet. Drogue deploys at just under the nose cone. Then at 1,400 feet, we have the main deploy on booster section and recovery. So the drogue is descending at there's so many. Oh, why did she do two? So drogue at the apogee, we have 10 feet of harness on the nose cone side and 40 feet on the avionics bay side. This is to ensure the 40 feet on the avionics bay side is to ensure the nose cone doesn't interact with the avionics or booster section at all. And we want the after the main descent, we wanted the booster to be actually at the top of the recovery stack so that it wouldn't have any chance of hitting any of the other components. So then after the main deploys, we have the booster attached to a 20-foot harness, and then 40 to the avionics bay, and another 40 to the drogue, and 10 feet to the nose cone, which we're hoping will have as beautiful a stack as we have for the other rockets. And then the descent velocities are as mentioned before.
This is just a quick bill of materials. We need quick links, swivel links, Kevlar harness, main chute, drogue chute, Raptor systems, and CO2 canisters. Those are the masses of each, and those are materials.
So, topic of discussion. So the drogue for, or the load for the drogue, the expected was used, or was calculated using OSCalc, which the main difference between OSCalc and DiffCalc is that OSCalc is what's called hop and jump parachute deployment, meaning that it does not free fall before deployment. So we need this opening shock factor to determine the briefing of the parachute time. So OSCalc takes parachute fill time and mass sort of bundled into this factor called SCK value, which is the opening shock value. So we've taken all that into account and had an expected load of 79.44 pounds for the main. And we have that split up into two values, which I can give you for the main and or for the two sections, based off of the masses of either of them. And for both of these, the length of the harnesses doesn't change the deploy loads, because the main factor is the masses and the fill time. And so once the parachute fills, the lines will go taut and it will immediately experience that load. So for drogue, we have the expected for the avionics base side at 37 pounds and the booster side at 37 pounds. So it's about an even split for it. Why is that even split for it? Oh, no, that's a lie. Yeah. So 29.79 pounds for the nose cone side and then 49.65 for the booster side. That's what's expected. And then for the max for the drogue, this was using PIF calc because the max or what's it called, the operations for what we're thinking would be the max deploy load taken under drogue is it doesn't deploy at apogee, but it says it starts to free fall. So we have that free fall experience, or the rocket experiencing free fall, so we use the PIF calc calculations. And then we use the max number of shock or of shear pins that we could have, and the max load that we could have with that. Oh wait, no, that was. I'm trying to think about how we did this like a month ago. So the max for the drogue is determined by the max shear pin value somehow that I completely forgot. But 256 split with the same ratio, about 207 in the booster and 48 in the main, or in the forward. And then the main is PIF calc again, 88 in the expected value and much larger, 547 for the max. And then under drogue, we have 101 feet per second and 21 feet per second under me. Oh, so and then energetics calculated to be a 13.6 grams for primary, energetic under drogue and backup 14.1, and then main 11.3, backup 11.8. But we are using compressed gas CO2 for both primary and backup for both deployment events. And the smallest commercial canister that we can get with the 1/2 inch threaded, which is what we need for the Raptor system, is the 23 grams. So we're going to use 23 grams for all energetics, drogue, main, backup, and primary, which is upsizing all of those values. We'll do ground testing to ensure that, but we did ground testing on similar values in Hodge, and we're confident in this ejection size or ejection energetic size. And then for our shear pins, the main concern is in the main size, or the main side shear pin value, because under drogue we have a massive size or a massive booster avionics base side, and then we have the nose cone, and the booster side is almost guaranteed to separate the main before or prematurely if we don't have an appropriate number of shear pins, which we calculated to be 11.3, and we're upsizing to 12 for 40 shear pins, and then drogue 3 shear pins.
Yeah, and just kind of building off of that, some of that testing we plan on doing, we want to do a lot of ground testing for CO2. We calculated that we wanted those values, and we're going to upsize to a 23 gram CO2 canister. And we just want to do a bunch of ground testing to make sure that is indeed not going to tear apart the rocket, that's going to get all of our separations correctly as we intend. And on top of that, those 2 flight tests I mentioned at the beginning of this presentation, we want to make sure that we can fly this rocket with those shear pins, with those CO2 canisters, and we have a complete success and a nominal recovery scheme. This is also gonna be a good chance to test the SRAM flight computers and confirm that our harness lengths are correct, minimizing our tangling or collisions. Manufacturing plan is pretty straightforward. On top of the mechanical bulkheads, we're gonna add our Raptor systems and then connect those to the flight computers on the electrical side. And there's also assembly of harnesses and the mechanical linkages. Integration assembly order is as follows. We're gonna connect the harnesses to bulkheads using the quick links. We're gonna fold and attach parachutes to harnesses using quick and swivel links. We're gonna coil and tape the harnesses. Then we're gonna connect the Raptors to the flight computers, load the energetics, and then integrate the entire rocket with shear pins and launch.
So for our recovery matrix, we have a lot could go wrong. We have the deployment fail just entirely, which is categorized as no deployment, which is total loss of vehicle, and we have it kind of likely because there are many operations that go into this this one event. And then we have some in the yellow of harness tangling or connection failures, and then one in the green, which is zippering. So to go in further detail, our biggest risk is deployment system failure, which is going to be mitigated through increased redundancy and for more quantitative development or deployment analysis, and especially ground testing and validating during test flights. And then the second red risk is drogue parachute tangles or tears during deployment. Tearing is a non-issue because we're using, again, the ballistic ultra high speed drogue and using long shot cords to maximize impact on load time and enforce adequate fire protection. And then same for the main. For the concern of the main parachute tangling or tearing during deployment, we're going to ensure deployment speeds is low enough to be safe, reinforce parachute if needed with parachute tape, remove sharp edges from the inside of the airframe and ensure adequate fire protection. And then for aft airframe separation from Avionics Bay at drogue deployments, this is another big concern, but we're going to mitigate that with the use of sufficient shear pins in the aft section and calculate based on worst case opening shock loads during deployment to prevent premature separation. And then we have connection point failing during breaks, which we're going to mitigate by calculating the shock loads and developing connection point breaks accordingly. And if the harnesses, or for harness tangling with chutes and airframe, we're going to wrap loosely or reef the harnesses loosely, tape with painter's tape, test deployment on ground, analyze test flight behavior, and we're going to use swivel links to prevent any harness twisting. And then lastly, body tube zippering. This year, Juliana did a lot of research into the type of harness that we'll be using, and she found this is so Juliana did a lot of research to find a COTS 1/2 inch tubular Kevlar harness that has COTS zone loops in it. So we've sourced that. We haven't gotten it in yet, but that has a really high load. It takes a really high load, and it also is much more fire resilient than the nylon shoes that we were using last year. But body tube zippering concern has been mitigated through analysis that the mechanical team has been doing with fiberglass shear analysis, and so that's almost a non-issue now, especially with a 1/2 inch wide harness. Yeah. Any questions for recovery?
Yeah. So you're saying you want to use 12 shear pins?
Yeah, we're going to ground test that. That was I think the minimum value that we could safely have was 8.
It just seems like a lot of holes in the airframe and a lot of, and have a hard time believing you need that many shear pins. That just seems more than I've ever seen in practice. I mean, primarily, what's the goal with the shear pins is to keep the airframe from prematurely disconnecting, and that seems like more than you really need to do that.
So the minimum number of shear pins that we would need to prevent the load, or to prevent the main from prematurely deploying with a nominal load or the expected load under drogue is 8 shear pins. We just put 12 as the number of shear pins that we are going to test on, because we analyzed the maximum load to be under drogue at a specific velocity. Oh, so we determined that we want to have a factor of safety for the velocity and increase. What did we have? So the velocity, the max velocity for the drogue deployment was 45 meters per second, and the velocity so we can have 8 shear pins, and we'll test on a variety of number of shear pins. I agree that 12 is a lot, and that is a lot of holes in the airframe.
Yeah, that's just my concern. I mean, the other thing you could investigate, although I've never used it, is potentially using bigger nylon screws. I don't know exactly how that would behave. I've generally only used up to 440s, but that would be another way that you might be able to adjust it without having to have quite so many shear pins. Anyway, so that was just my concern with that.
Do you think that 8 is still a rather high number?
I mean, it's more than I normally do, but it's probably reasonable. It seems more reasonable than 12. But you know, I've usually found, I mean, I rarely use more than 4 or maybe 6, but I'm, you know, probably not quite as heavy an airframe as what you're talking about. So it seems like 8 probably would be adequate, but the best thing to do is to test it. See if you can, better yet, you know, see if you can figure out the braking, you know, what strength is, you know, what pull is gonna take the airframe apart, and if you do some testing, hopefully you could figure out, you know, whether it's adequate.
Yeah. Thank you. We'll also look into larger shear pin sizes.
Yeah, I think that sounds good. Yeah, we'll look into the larger shear pin sizes, and then also double check them out. And of course, back everything with testing.
Yeah.
Nice. Yeah, I just wanted to add on to Sam's thing. Is there any like conceptually, why did the number of shear pins go up if the airframe mass is kind of similar to last year's?
So it's because of the deployment positions. So the drogue is deploying first and deploying at the nose cone. So you have a heavier section that needs to stay together, versus last year we had the drogue at the booster section with just the nose cone and the avionics bay needing to stay together. So the nose cone and the avionics bay mass are relatively small compared to the booster section. So the number of shear pins is the weight of the booster.
Got it. Okay.
Yeah, no, that's right, because you actually have to take the whole shock force of the drogue deploying in the shear pins because of how your configuration is. I mean, the other risk, frankly, is that with the shear pins is that they don't deploy, and that's a worse condition. So that's the other thing to think about.
We'll definitely ground test that, but an
Yeah.
additional concern that I'm thinking of is we need to ensure the number of shear pins that we have is a safe number before we drill any holes, because we can't test 12 shear pins and then realize, oh, we drilled too many holes, the
Right.
airframe isn't safe. But maybe if we drill 8, then we need 12, then that ratio of the distance of the shear pins is on. But that's a whole it's a conversation.
Yeah.
I will say, with good bond prep, I have full faith in Sheelan and the airframe team to be able to patch up those holes and probably get some of the strength back. So.
Yeah.
Also makes sense that like the limiting factors, the shock, because I know there's last year, I think it was the limiting factor on ascent was motor burnout for the drogue shear pins. I'm not entirely sure. Okay, that's all set. I'm happy with that.
Yeah.
Sorry, Sam, do you have any other questions? If not,
No,
go ahead.
that's good.
Okay, slide 100, bill of materials. Just wanted to double check, what size chute are you using this year?
What size chute? 96, so that we have longer time to collect the data for main, and then same drogue, the 36 inch.
Okay. Okay, cool. And that's the parachute compartments properly sized for that?
Yes.
Nice. Okay, and then last set of questions. Yeah, sorry about this, but can we go back to slide 102, please, for the loads? Also, side note, I'm very excited to be seeing the like CO2 only. It also seems like there's a lot of margin on there, which is very good, and so hopefully shouldn't be too much worry there. Yeah, I was just sorry. Actually, wait, yeah, can we go to the deployment mass calcs first on slide, how is that also slide 102? Oh, I might be looking at the wrong presentation, slide 103, okay. Yeah, do you remember what it was last year on main? Was it higher? Only asking for like a sanity check. If you can't find it, doesn't really matter. But only asking for a sanity check of is everything set up at least in the realm of reasonable possibility.
So,
I know the ground test will take care of it.
The main last year for black powder was 4.4, which is higher. Oh yeah. So is your question, why is the drogue higher than the main? Or are you sanity checking from last year?
I'm just sanity checking that the main isn't too low, because it seems, based on vibes, a little too good to be true.
The volume isn't that big because you've got a motor in there.
Yeah,
But the
pressurizing
volume
the
shouldn't be
motor,
that big with the drogue either. So, yeah.
Well, the volume of the drogue for this rocket is larger than the main because it is housing the payload as well. So it's an extra long length,
Yeah.
but then the payload takes a little bit of the volume away, but you still have the extra volume around the payload that you have to pressurize.
Got it.
Yeah.
So that's why the drogue is larger than the main.
But in either case, your cartridges are going to be huge, so your canisters are going to be huge anyway. So.
Yeah.
Okay, nice. Yeah, I'm happy with that. If you want to go one more slide further to 104, I guess. The loads. Maybe 102. I wrote down 102, sorry.
Oh, back.
Yeah. Okay, perfect. Thank you. So OSCalc is hop and jump with no free fall, and PIFCalc is from free fall, right?
Yes.
Okay, got it. What's the difference between expected and max loads?
So expected is at so for drogue it's at oh my gosh, apogee, being it's at 1400 feet. Max for drogues is oh, I just remembered what it was. Oh, so we spent some time discussing the number of shear pins, and we decided 12 might be possible. So we decided that with the 12 shear pins, the load that could be like the max load that the main could take from the drogue is 256.18.
So does that come from the number of shear pins or from the like parachute deployment stuff?
That comes from the number of shear pins because the worst case scenario for the drogue is just the drogue deploys maybe at main, like it's not very discrete. We had a hard time figuring out like what value for the maximum velocity at which the drogue deploys could we save the rocket. And so the limiting factor there was the number of shear pins for the main, because at a certain point, the load for the drogue, if it were to deploy, it would also deploy the main.
But deploying the main is not a problem if it's a like emergency deployment. But if you deploy too high and the bulkhead fails, then you're cooked. Well, I guess if the main comes up too, it's fine, right?
Yeah, I mean.
Sorry, my question was more like, I just want to be sure. Maybe it's just like what the words chosen are, but if you're expecting a load, but like the load could be higher, the like good design practices to design to the maximum expected load or max design condition or whatever you want to call it. So I just want to make sure that, yeah.
You're saying we should have a limiting factor for the drogue that's not dependent on the shear pins, maybe dependent on the velocity or the position.
Yeah, I think it would be a good idea, and I don't know what that number actually is, but to have a like this is the highest load that we expect to come down the harness from the drogue, and this is what Mechanical's doing their analysis based on,
I mean,
and
so
make sure that
the hardest load that we could experience from the drogue is if it were to deploy like 100 feet from the ground after free falling ballistically. But that's not like the rocket's not going to survive that. So the number that we gave them was based off of the shear pin value, because that is a concrete value that we say, oh, this is a failure point for the rocket that we can say this will have a problem if it deploys up until here. But any other point in the rocket, like it's a goner.
But goner with bulkhead failure is actually goner. Goner with shear pin failure and main premature deployment is like goner from a mission goal, but from a safety perspective.
That's a rather like circular decision then, because if your failure point is the load of the bulkhead, then we tell Mechanical, oh, build it as beefy as you can, and then the drogue will be fine.
Well, no, you pick the velocity at which you want to deploy, the like max acceptable. That's what my question is basically like, is the max? So the max is what the shear pins can handle, but what's the so the expected is then really the like expected max?
The expected is nominal, is apogee.
Okay, so if the drogue deploys, say, like half a second after apogee, the expected load would be higher?
Yes.
Okay. Yeah, my advice would be to pick some time after apogee or velocity after apogee and set that as the max expected.
The expected is in OpenRocket, the simulation of we set the drogue to deploy at apogee, we simulated the velocity and the position at which the drogue deploys, and we set the velocity to be what the OpenRocket simulated it to be, which was 30 meters per second.
At apogee? Okay, nice. Okay, that I'm happy with that setup for getting the expected. And then yeah, I'd strongly recommend doing the design based on some maximum deployment load. It's up to up to you guys on how much risk you want to bake into that. I know the like thing with CARM 2 years ago was, I think we said like 2,000 feet after apogee was what we designed the drogue to, which was kind of ridiculous. But somewhere between designing directly for apogee and for 2,000 feet after apogee, there's a point at which should be the like design condition, which is like the acceptable variation, the like latest that you can deploy the drogue and have the bulkheads be happy, and the rest of the internal structure. It's up to you guys how much of a buffer you want to add, but there should be some buffer, be it like
So we can
half a
say the rocket will survive if the drogue deploys after 2,000 feet of free fall.
I think what you should look at is in the open rocket sim, you can set the drogue to deploy like a few seconds after apogee and then just get the velocity from that. And that like amount of seconds after apogee can be your buffer, and you can decide how much of a buffer you want to have there. And then based on the velocity at the end of that buffer time, the load you get from that deploy load there is what informs the like maximum design condition for the bulkheads. And
How do you recommend choosing that time afterwards? Because I think Cisco's point is that can be
Yeah,
very much up to debate. Like,
that is what we did. That's exactly what we did for main, and then we chose a value that would give a load in a reasonable range for mechanical to build. Okay. But for the drogue, we say if you have a velocity within that buffer, say it deploys after 2,000 feet of free fall, but then you're sure to have the main prematurely deploy after that, then you're giving mechanical a value of with a limiting factor with already error built into it, with already something has gone wrong if we reach this value.
yeah, so that means that the buffer has to be somewhere between what you have listed as expected and max. So that answers the question of like what could be the max that we set as the buffer, is you want a buffer that's going to give you the load at deployment that is either below or right at that max that you get from PivCalc.
But if the limiting fact, like if you're saying that I don't understand then why we would have the maximum be below the velocity that we put in for that 256 load. Why not just right there?
Yeah, you could do it right there. Might as well just do that. The only thing is if you think that to get to that load, the max, the one that's written as max PivCalc, that 256, if you think that getting to that load is too conservative, then you guys can decide, okay, we're okay accepting a bit more risk. We've looked at our deployments in the past, and historically they've been within, I don't know, 0.4 seconds of apogee, and something like that, and you like want to play it sporty, then it doesn't have to be all the way to the max. Otherwise, yeah, it makes sense to just set it at the max. I will say there's the like offset in time between main deployment on the RRC3 and backup on RRC3, and if RRC3 is flying as backup, that is nominally 3 seconds, but I've seen 3.15 in practice on, I think, CARM flights 2 and 5. So yeah, something being like 3 seconds after apogee, that could be your more sportier version, and then the less sporty version, the most conservative one, is to go with the like max that you could possibly get from PivCalc for drogue. Does that make sense?
Yeah.
Nice. Yeah, no, sorry. I know it's a lot of like circular stuff and confusion, and someone needs a load and then the like loads don't line up, but then it's a different expected setup. But yeah, if you have the chance to do that, recommend that, and then that way mechanical can like be sure that if stuff does go wrong, things can be okay. And the last thing I have on this was, so I remember we had similar discussions on CARM and on Hodge also, with like not too good like outcomes that weren't super concrete. And I was thinking how can we make them more concrete? We have flight data from CARM Flight 5 you guys hopefully have flight data from KINDLEVAN Flight 2, and what would be fantastic is if you're able to like correlate that data to the predicted data, and then kind of get an idea for how close the calculations are. Yeah, how close the calculations end up being to real life. Like for example, I remember getting on Carm Flight 5 the like drogue axial load that the AVBAY, like AVBAY and booster section saw was I think 109 pounds.
Are you using accelerometer data for that?
Yeah, yeah, just like F equals ma it, and then it's like a more hand calcy version, but it should get like a ballpark of this is kind of the range or like an idea of the force. Like that 109 pounds that I got for Carm was on Carm Flight 5. Like there was a little bit of smoothing in the acceleration data, so there's a little bit of like the peaks get cut out there. But
109, was that drogue or main?
that was on drogue. Main was 60.
That was a beefy rocket.
Yeah, it was heavy. Yeah, so something like looking at that data, looking at the KINDLEVAN Flight 2 data, which hopefully is good and should be a very good resource for something like this. That should give an idea of like, yeah, ballpark, are we underestimating, overestimating, and then hopefully that can give more confidence too on the like.
That's a good idea. Any other questions?
No, also sorry for if I'm holding up pizza.
You're good. You're good.
Yeah, hopped on a free fall. Okay, yeah, that's what I had for me. I'm excited to see it. Great job. Also, yeah, I don't remember if I said this already, but I'm really happy to see the CO2. That'll be so much easier to clean, and the payload will be so much happier, and the chutes will be so much happier, and sounds like a great choice overall.
All right.
Good work.
Cool. Any additional comments, Sam?
I was just gonna say when I have had experience with late deployments, it's usually the failures are usually usually it takes the shroud lines off of the drogue. And I would also say, you know, it's usually more zippering than pulling directly on the bulkhead. But
So
you know,
you think the limiting factor would be like the load that the shroud lines could take?
well, I mean, the shroud lines will do what they do. I mean, if they, frankly, the drogue shredding is actually not been so bad because usually because rockets come down a lot slower when they're broken apart anyway. So it usually actually turns out okay when that's happened. The bigger issue is if you have the main come out late, that's a big problem because if you pull the shroud lines off of that, then you're going to come down really hard. Best thing is to not have that happen.
Yeah. The other thing is for the
yeah.
Go ahead.
Go ahead.
The drogue this year is still the same as last year with like the ballistic nylon, right?
Yes. Yeah, that's not gonna.
Yeah.
Put it through a paper shredder.
Yeah.
Well, that's a good comparison benchmark that we could look at as well. Thank you for the insight on the load calculations.
Yeah, thank you.
Yeah.
Anything else?
No,
Yeah,
that's
just
good.
one
And thanks for
question.
the patience. Oh, sorry.
No, it's cool. It's how much pizza is left?
Okay, moving on.
Solid single slice, I think.
Oh, it's all.
0. Sorry, Daniel.
You missed your chance, Daniel. Okay. We're going kind of overtime. Are you guys doing like a 5-minute break? Okay. We'll come back in 5 minutes to go with electrical. So use the bathroom.
3:07.
Use the bathroom. Yeah, we'll be back at 3:07.
Where's my pizza?
You're not here. All right. Good to go.
All right, hello. Catherine, electrical lead. And start off, we're gonna go over the general architecture for electronics. So for the electronics inside the rocket, we have 3 SRAD boards. So the first one is KINetic, which is our main flight computer. We'll have 2 copies. One is designated for collecting and sending data to the ground station, as well as controlling ejection. charges. And the second copy is specifically for controlling the deployment of air brakes and collecting in-flight data. The second board is the solar board. So that's going to be measuring the current draw from the payload as a function of altitude. And as discussed previously, we're also thinking about adding another set like an IU just for more data that we can collect from the payload and just for analysis of that. We also have a third SRAD for regulating the camera voltage so that we can provide a steady power source for the cameras. We then also have a COTS board, the RRC3, to control backup deployment, which is also required for. So for our cameras, we have RunCam 2, RunCam Split 4, which Ben's going to talk about for detail later on. We also have a COTS GPS tracker, which is required. So here's the system block diagram of all of our electronics inside the rocket. So we have, as mentioned, the 2 copies of our main flight computer, one for the air brake board, which is the air brake board, and it has an IMU barometer, IG accelerometer, 2 temp sensors, a GPS, a magnetometer, and an SD module. And the second one for transmission has all of those sensors plus the LoRa. And then the solar board, the camera voltage regulators, and then the other 2 COTS boards. So just a design overview and some goals. So our main goal is to log onboard sensor data, get successful collection of data from all of our sensors, and also send this data in real time down to the ground station. We also want to make sure we can successfully control the air brake deployment as well as our ejection charges. And then we want to collect payload data and make sure we can regulate camera voltage. All right, so this is a picture of the board, our main flight computer we just recently ordered from JLC-PCB. So yeah, it's pretty nice. So just to talk about some improvements from Plate. So Plate before, there really wasn't any complex or more helpful way for debugging visually beyond some LEDs that just indicated the GPS was on and then power to the board. So for this new version, we have an LED 7-segment dual 7-segment display for error codes and also potentially reading out some sensor data, which is great for making sure validating our sensors are working, and also could be helpful for air brake state machines. Another thing is there was no SD module on the PCB itself for Plate, only a separate breakout, which was kind of finicky. The connection wasn't great. So this time around we added it onto the PCB itself, which will hopefully make a more secure connection. Another issue was the board would not jumpstart the program without holding the flash button, which we encountered during the launch last year, over the summer. And so this time around, we should have a flashing scheme that automatically kickstarts the program without needing to mount this button. So we also replaced an IMU, which was very hard to set up. So this new one should be easy to access. It has a good data rate, and yeah. And then we also had only one temp sensor that was just measuring the IC temperature, internal temperature, so not very helpful. We wanted another one to actually measure the app bay. We added that. It also measures humidity. Okay, so overview of the board. It's a 4-layer board, so it has a front layer for signals, ground power, and the back layer for signals. We have 7 sensors as mentioned. So here's just an overview of some of the parts we're using. You can see, I don't think it updated, but I put the had put the data upgrades on there. Can't see that anymore. But yeah, I think for the IMU it's like 6,400 hertz or something, and then for the barometer it's 40 hertz. We also have the LED display at the bottom, as you can see, which is a dual 7-second display. Pretty cool. So here's our schematic with the new sensors that we added. We also have some power management at the top left corner, such as a bridge rectifier to prevent any sort of backwards current to damage the board. And we also have a LED to indicate power, successful powering of the board. And you can see the display stuff at the bottom. And we also have a USB to UART converter at the top right, which helps us just easily interface and flash the board. So in terms of the use for air brake deployment, this is just a very simple block diagram of how we plan to wire things. So we have a servo motor we picked out from Servo City, which has 3 wires coming off of it, 2 for ground and power and 1 for the PWM signal coming from our flight computer. So the PWM signal should be able to use the width of that modulating, and that should tell the motor how far to move, which will then control the air brake system. And we're also running both the flight computer and the servo motor off of 9.6-volt batteries, which I'll talk more about. Here is the recovery diagram. So this is for the meeting that's controlling the ejection charges as well as transmitting down to the ground station. So we have it's similar wiring to last year where it's color coded. So blue is going to the main chute in the back, and then green is going to the drogue chute, and then we have blue as well, and then we have red going to the board, and then green going to the COTS board. We also have switches for COTS and SRAD board. All right, so we also have a payload board, which June designed and is working on. So just some details about that. It measures the current from each of the 4 solar panels in the payload. And we're planning on using a ESP32C3, which Lily was able to get working for the IMU board last year. So yeah, we're also gonna include a barometer and potentially an IMU, as well as an SD card reader for logging the data. So right now we have a schematic, which we're going to continue working on before going into designing the PCB. And there's going to be testing with a breakout version, I think, and a small scale prototype, and then some more testing by just passing currents into the sensors and making sure that we're reading valid data. So here's a schematic that June developed. You can see it's the C3 module with the microcontroller, and then there's four sensors for reading the current that all use SPI. And then there's the barometer from our board, the main board, which is using I2C. And then we have the SD card module, which logs all of this data. So in terms of manufacturing all of these SRAD PCBs, we are ordering from JLC PCB. So we're ordering all these boards from them, and then they come with these stencils that we can use to easily just apply all the solder to the pads on the front and the back layers. And then once we place all of the surface mount components, we can put them right into the oven, reflow them, and then for the back sides, some tape components stay on. So we're actually, just to give a current update on where we're at for the main flight computer, we have the boards from JLC PCB, And we just need to order some Kapton tape and before we start assembly, but that should be happening pretty soon. So we can start testing the testing and debugging process, which is exciting. So just to talk about batteries and power management. So last year we used lithium ion batteries from Urginex. I think they were 7.4 volts, but this year we're no longer allowed to use those batteries. So we're switching to the LIFE PO4 9.7 volt batteries from B&K, and they fit the required form factor and they're rechargeable. So they should work pretty well for all the applications we need. And in terms of management and testing, we'll pretty much keep them charged to around 9.6 volts. And then once we charge them closer to the launch, we'll obviously run voltage checks. We voltmeter, making sure all of our batteries are around the correct voltage. And then we'll also perform tests on the battery health by just doing a full discharge of our batteries, which should have a capacity of around 6 amp hours. So, and then additional note that we'll have patches in the avionics bay similar to last year, which makes it easy to swap out these batteries if necessary. All right, so some of the tests that we're going to be doing is just sensor verification. So this is pretty easy. We can just practice hooking up our the computer, flashing board, and make sure that we read back valid data. We can also do ground testing. So this is going to be really important for if we're flying our computers active. So we'll need to make sure that our SRI computer is correctly firing the charges. And then, eventually further on down the line, once we've done extensive air brake testing and sensor validation, we'll fly all of our electronics active with air brakes. So in terms of integration, just to give you an idea of where all of our electronics are located. So KINetic for transmission, camera voltage regulator boards, and ROC3 are all in the av bay. And then KINetic for air brakes is mounted in between the booster and the av bay, so the air brake mechanism. And then the solar board is mounted in the payload structure as already mentioned. So in terms of just integration, we're going to be mounting all of our boards with standoffs, and on launch day, we're going to make sure to verify continuity for any ejection of boards, and then board power as well as any batteries. And we'll have external switches to power on both boards, and also Matt's going to make sure to verify telemetry. All right, so in terms of risk matrix, we have the highest risks being, or the most likely risks being falsely firing circuits. So this is mainly to do with recovery, point of parachute, as well as the air brakes. And then further on, there's some worries about telemetry failing. So yeah, telemetry loss, we can try and reduce that by doing extensive range testing and also testing with the ground station. In terms of mitigating the falsely firing of the circuits, we can run through the air brake state machine. Ground ejection testing is going to be really important to make sure all of our sensors are working correctly, and then try and test launch active with air brakes before competition. Another worry is running out of battery power. So obviously we can mitigate this by checking, as mentioned, the health of our batteries by doing a full discharge and then charging to their nominal voltage right before launch. And then sensors, obviously we'll do extensive testing of our sensors, make sure they're robust under the flight conditions, and replace any of these if we don't think they're going to meet our requirements. Wires coming out is also a worry, but that can be reduced by just having better wire management. And then reverse polarity is really a big concern because we have hardwired boards that don't allow that to happen. So some open issues. So we were able to test PETA plate this semester, which was great because we got successful data collection from an SRAD board from the main flight computer, which was SRAD for the first time. But we did find some issues with the data, such as the sampling rate being too low. So we didn't get a lot of granularity in the data, which means it's not as helpful. And especially for air rate purposes, we're gonna need that to be way more accurate. So we're gonna help mitigate this by calibrating the IMU ranges, which I think were incorrect as well. So we didn't get that spike in acceleration either. And then, as mentioned, increase the data sampling rate. And also testing active injection charge deployment, hopefully sometime soon. And then also developing the solar voltage regulator boards and testing them. So in terms of schedule to completion, as mentioned, we're right around December 5th. So we're starting to assemble Mini, and we'll hopefully finalize this assembly early January and be able to start testing. So we'll also try and finalize any first versions of external boards, so the solar panel board and the voltage camera. And then we're gonna hopefully conduct ground ejection testing around February 2nd, but potentially before that. And then finish assembly of all external boards by the end of February, so we can hopefully test them in the rocket at some point. And then March to April, we'll actively test the main flight computer with air brakes and all of the other external boards. I was hoping to have Ben talk about cameras, but slides.
Slides got mixed around. Whenever a bag goes up, we're gonna refresh it. Just go back to the cameras.
Yeah, so that's all I have for electrical.
I got some questions. Well, I mean, just going back to the solar board, I'm just curious. It's just the ESP32C3 that's being used, right?
Yes, it's a C3.
Okay. Yeah, all I wanted to do was just look at the schematic to confirm. I just wanted to mention again, yeah, you should throw in a couple more sensors because of the fact that, you know, the what is it? Current draw shouldn't be, I don't think it's a safe thing to assume that, you know, current draw is completely dependent on air density. But that aside, I was curious about the traces that you have for what is it? Those terminals that'll be doing the ejection charges. Are those kind of copied from PETA?
Let me just go back to. Yeah, so we have the pretty much same setup as PETA from last year, which I believe was all set in terms of hardware. But we never got around to testing it.
Yeah.
He's telling me. So
I think Miko remembers this. We got like a single test just like to prove that it could fire the circuits, and we found that it could. It's just that we never were able to do like any actual ground testing with that.
That was the night we lit up the LEDs, but also fried it when it pulled power through the USB, right?
Yes.
Yeah. Yeah, we were able to fool it into lighting the LEDs, but we didn't get the chance to do the like vacuum testing.
So that's, as mentioned, that's something we're gonna try and do. Definitely.
I mean, even before vacuum testing, I would just confirm that those traces are large enough, or like that it can actually deploy an ejection charge before doing any kind of like apogee pressure testing, you know.
I mean, our sorry if I'm talking, but like our theory says that it should, just based on like calculations. But yeah, that's a good plan.
Okay, cool.
It's pretty easy to do that.
And then
and from the test Lily and I ran, it should, like it put out the current that was needed. It should just need to be connected to a explosives. So
Okay. And then one thing about the schematic is this is probably pretty minor, but you're still using a rectifier for any kind of reverse polarity issues, right? Was that a yeah? I didn't hear.
Yes, yes.
Okay, cool. I just wanted to bring up the fact that that is low key inefficient. I was just gonna mention that maybe you could use a stocky diode, or some sort of MOSFET instead, because you do need like like up to 2 volts just using that thing, because it's built more so for AC purposes. But uh that's up to you. It's just might be a bit of a space saver, but it's nothing all that crazy.
Okay. We shall note that down. So we have some, just in terms of future improvements, I think we're at a pretty good spot right now for like all of our sensors working.
That's good to hear.
But I think in
yeah,
terms of
congrats.
adding on to the board what you mentioned, and also potentially more components for air brakes debugging, so maybe some sort of button for like steam machines and something along those lines. And some minor changes like with labeling and stuff like that. But overall, I think functionality wise, we are feeling pretty confident that all the sensors are going to work. It's just a matter of being careful with the assembly process, making sure we place all the components correctly and don't screw anything up.
Cool. That's good to hear.
Another question?
Yeah, that's it from
sorry,
me.
I have a few. Thanks, Daniel. Also, to Daniel's point about adding additional sensors, the other thing I forgot to say earlier, I think, is that if you do have an accelerometer or an IMU of some kind on there, then you don't have to rely on the accuracy of the clock. You can just you can time the data to the spikes in acceleration at liftoff and then start from there. So it's helps with the data analysis at the end. But could you go back to slide 129, please? Also, huge congrats on all the sensors working and on getting data from PETA. It's a big win.
Yeah,
and especially on having the board done and ordered already. That's
I mean,
really
it
nice.
was an unfortunate end to the board. But, it was honestly just one minor fix, was the flashing issue, which we fixed. Everything else kind of. Also, Matt developed a program for flashing, which was great. So.
Nice. Yeah, no, great job on that. Fantastic. Okay, yeah, for this slide, I was just curious, what are the plans for recreating flight conditions in ground testing?
So I know that at least we discussed some sort of drone. I think Ben and Lily were talking about this too, but having some sort of drone that you can control remotely to try and simulate some sort of flight trajectory and test that the sensors are getting accurate data that way. Besides that, I think that was our main plan. I think we can always just buy a drone online or something. They wanted to SRAT it from scratch, but I think there might be easier ways to do that.
Can I throw up a suggestion for a means of testing this?
Yes.
So we don't have a large data set. We have flight 5 from CARM and then 2 from Hodge. But I think what you can do is maybe, I guess I wouldn't say extrapolate, but I would say maybe kind of use those for as a basis for Monte Carlo simulations, and then see how robust your state determination algorithm or criterias are for figuring out which state the rocket is in.
Yeah, I think this is a good idea. I don't think we need to. I think we can just use like previous data or use what we have to kind of feed it into a simulation that way.
Yeah.
Yeah. And then any bonus points, of course, for stuff where you can like actually physically change the state, like hooking it up to a vacuum or I don't know, artificially increase the temperature with
Yeah, we
like
did
a soldering iron or something.
we did have some sort of issue the last time we did ground injection testing with with the sensor, which we think could just be a faulty barometer on the RC3, but it
And then the hypothesis was validated when we flew it. It didn't go off.
yeah. So that's something I just wanted to point out, but we're doing lots of ground ejection testing to try and rule that out as an issue in the future. But yeah, that RRC3 ended up not deploying the second launch, that it ended up landed in the water. So
Ah, damn. Yeah, no, definitely, I definitely encourage because I know one of the things we got stuck on at least 2 years ago, somewhat last year, was like the rest of the rocket not being ready and like waiting for that to test. And so yeah, I definitely encourage wherever possible to like make your own testing setups that don't need the rest of the rocket before other parts are ready, so that there's less like waiting until we can do a full integrated ejection test and maybe like can we do it on a smaller rocket, small thing.
another idea that I was thinking is flying electronics in smaller rockets, like L1s or something, just to get
Yeah.
data.
Yeah, no, it's a great idea.
So,
Like even less than that, like because that requires you to go to launch. Like maybe even just hooking them up into something that you can like throw up really high in the air or silly things like that. I don't know. Okay, I'm happy with that. Can go to slide 132, please. Oh, I am sorry. I was looking at the wrong thing. For risk number 5, wires coming out. Any plans for wire management? I had a couple questions here. I think for the wire management, the questions were like, how are you planning on have them not come out? Or is the management just for like routing wires nicely?
I think the wire management was mainly like the bay, like what was mentioned.
Okay.
Bunching them in some way that they're not getting tangled or like snagging other components. So I think having some way of like grouping them together and keeping them out of the way of the main bay.
Okay, yeah, sounds good. And then I think Ben mentioned hardware in the loop testing. Any plans for that, or should I wait for avionics and stuff like that?
I think we're gonna cover that in avionics mainly. Everything.
Okay.
Air brakes, state machine stuff.
Okay, cool. And then yeah, last question is there any sort of have you ever done any sort of like power budget or current draw calculations for the air brake motor? Because the one thing I'd be worried about is if it like takes a large amount of force from the motor to like retract, deploy the air brakes.
Yeah, so we picked out a motor from Servo City, and we have it with us, so we could technically hook it up and try taking some measurements from that. But I think until we have the actual air brake mechanism, we can't really test how much current it's going to draw moving it. But for now, we can try testing it with something else.
Okay.
Yeah, we do have a motor.
Hopefully it's on the spec sheets, right?
Yeah, there's specs on it. I don't have it.
Oh, okay. Yeah, you don't have to have it as.
But
if it's sorry, go ahead.
It's also going to be powered separately from the board as well. So.
Yeah.
From Steve battery that the other electronics are drawing.
Okay, sounds good. Yeah, as long as the like wires can handle that properly and the batteries can survive that. That sounds good. Okay, and then last question on the next slide, please. And then I'm done, I promise. What was the sampling rate on PETA and what were you shooting for with Panini?
So for PETA, it was very low. It was like 2 times a second.
Oh my God. Oh.
Yeah. So we ended up getting like 4 samples of 2Gs from the IMU. Obviously, is I think a combination of the way that the IMU was set up because it has different ranges, so it can go up to 60.
Yeah.
So I think that's obviously something we're changing is that calibration, but also increasing the data sampling rate. I don't think we decided on it, a specific rate yet, but much higher than 2 times a second. Basically, as fast as it can go.
Nice. Yeah, nice.
Definitely not high enough to capture very interesting changes. So I think it's a combination of that and the settings on high.
Okay, sounds good. And yeah, I think there is from a while ago, I remember talking to Daniel about like the settings on the accelerometer and how we get like the much higher, I guess, higher resolution when it's set to the max out at 2G. It's obviously your call on whether that's worth it to you or not, as long as you have a high G accelerometer as well. But I remember the like temporary conclusion at the time was that the data from the high G accelerometer was still really good for our sampling rate, and we didn't really need to worry about the low G. But again, that's up to you. Depends what sampling rate you guys end up getting. So.
Yeah, the high G I think was more accurate. So yeah, we can look into whether or not it's I think the high G is more important.
Nice. Okay, yeah, that's all I had. Fantastic job. Super excited to see the data from these. And yeah, congrats everyone.
Yeah, right now. Cache escape and represent. Yeah.
All right, so just to talk about the onboard cameras, it's relatively similar to what we did last year. The only thing that we're doing is we're trying to sort of streamline the cameras more, have them take up less weight, as well as higher quality, as well as this year we are going to be attempting potentially some live video transmission. So for our onboard cameras, we're doing 4 cameras that are being housed in 2 different modules on the side of the rocket. So that means on either side, we're going to have 2 cameras facing up and 2 cameras facing down. The goal of that is that hopefully we'll be able to see all 4 air brakes using the cameras. So if anything does go wrong and we're able to recover footage, we should hopefully be able to have some failure analysis. This year we plan on running 3 run cam split for V2s. We used one of those in the rocket last year. They're relatively small, lightweight, power efficient, which is why we chose that. And we're also using 1 run cam Wi-Fi link 2. This is something new we're trying out this year with live video transmission. So that camera will be attempting to broadcast video at 1080p, 60 frames a second, or 5.8 gigahertz channel, and we'll have a receiver down at our ground station to receive that. In order for that to happen, we will be doing a bit of range testing before that is fully implemented. And if that does succeed and we're able to basically, show that this can theoretically work, then we'll be doing that at competition.
Can I make one note? Yeah, this is not like our telemetry setup. This is a separate system that's kind of all COTS. So this is not like when we're talking about like our telemetry for astronaut boards, totally separate. We're not doing this ourselves.
So exciting. So happy to see it.
So just to talk about like sort of the systems that are supporting cameras. Calculated the theoretical worst power draw that we should be getting from these cameras is a consistent 12 watts. This is something I definitely want to test once we have all the cameras ordered from RunCam. We did also get a slight discount from RunCam, which is really great, 10% off. Makes a difference when you spend that much money. But so we're definitely going to test that based on the different settings that we're going to be going on cameras. Obviously, resolution, frame rate, and how much transmitting power we're using are all going to impact that number. So that's something we're going to verify. And I think in terms of worst case scenario planning, we should try to aim for about 2.5 hours of runtime for the batteries that we have for these cameras. You can obviously talk that through, but I think that's a good number in terms of if the rocket is stuck out there on the pad for an extended period of time, whether there's a hold or something like that, we'll have more than enough time to, still have those batteries completely charged, so we don't go up without any battery on those. And this battery system is going to be completely separate from all of our other battery systems, so that this is a very, non-essential system. We wouldn't want the rocket not to work or air brakes not to deploy because our battery or our cameras hogged up all the battery. So this will be totally separate. As of right now, I think we're planning on doing lithium-ion batteries just because they are the most energy dense, and this is obviously the most we need the most energy for the cameras compared to other very relatively low power boards. So we're using lithium-ion batteries for that. About 30 watt hours is what we're going to need, assuming that 12 watt figure is accurate. Obviously, we'll make sure that is through testing. And to address the issue last year of potential thermal throttling from the cameras, this year all of the cameras or the camera boards are going to be mounted open air inside of the rocket. And that any sort of convection currents that's going on in the av bay should be enough to cool it, as well as the one camera which does, you can see pictured there, which does have a more significant power draw. The Wi-Fi link to the one that's actually doing transmitting has its own fan on it, so that'll help circulate air within the av bay as well as keep that camera specifically cool throughout flight. And on that,
Awesome. Let's go ahead. Okay, so we have two computers on the rocket. They're both called Panini because they're effectively the same PCB, but they have very different uses. To go over the flight computer first, or the transmission computer, this is the one that's going to have the goal of reading all sensor measurements, which we're successful with. That's the IMU, barometer, high G, etc. And then what we're going to do is actually determine the state on the rocket. And the reason we want to do it here as opposed to the ground station is because if we imagine that the rocket is consistently collecting data from when it's on the launch pad to in flight, we're going to have built up a pretty accurate and substantial state that's consistently iterated upon. And if we were to send these raw data values down to the ground station instead of this state, if there's gaps in it or if there's packet loss, that might affect the accuracy of our state on the ground. And so instead, we're just going to send states pre-calculated up on the rocket down to the ground station to use there for when it tracks the, when I say ground station, I mean the rocket tracking antenna, and I mean the ground station. So we'll send it to first the rocket tracking antenna, which will compute, I'll get into that later, related things, and then we'll send it to the ground station for visualization. Before it transmits though, it's going to timestamp the state, convert it to bits and transmit it to the ground. We're going to figure out if compression is needed. May's been working hard on that, but we'll figure that out during range testing in January. And then after it timestamps and sends it down, it's going to write that state to local storage. So we can look at it later and then repeat. The transmission protocols are going to be custom ones with the LoRa. We haven't determined what the final product will look like. We've experimented with just getting transmission working with just default parameters, but like things like spreading factor or bandwidth will be decided in January during range testing. There's an APRS formality for how you organize the data that the MCC uses while we're there, I think. I don't think they require you to follow this, but I think it's a standard that we can choose to follow if we so like, because then anyone that knows the APRS formality can see our data and make sense of it without actually knowing our specific organization of it. I'm sorry, of our state that we transmit down. This is going to be developed in the Arduino IDE. The ESP IDF will be the final product. The sensor reading modules are a combination of custom code and also existing libraries. So like Radiohead for the LoRa module and the Adafruit GPS library for the GPS. Before we start, we're obviously going to do a health check on the sensors because if they're not working, we would like to know. This is more important for the air brake one, and I reference it here even though we're talking about the transmission board because up till now they're going to be effectively the same. So if we get any information that the sensors aren't working, we want to terminate the air brakes from functioning. Again, the compression procedure will be used if we need it. So this is what we were talking about earlier about sample rates and transmission rates. Each sensor is going to be tuned to a unique sampling rate that makes sense for that sensor. So for the IMU, Catherine and I were looking at the data sheet, it can operate all the way up to like 6,400 hertz. We might not use that many, but for like the barometer, it's gonna be much less. So what we'll do is we're gonna have all these sensors reading at their optimized frequency. And then what we'll do is we will have them feed into our state at their own selected frequency. And then once we have that state, we'll sweep through and grab from that state at a frequency that matches how often we'll transmit. So to be clear, we'll have every sensor on its own frequency. The state will be updated by each of those, and then we'll transmit on a unique frequency separate from all the other ones. And this will not be a frequency that we're like, this frequency we send down, or this transmit frequency is not based on how fast we compute the state, but it's gonna be set ahead in time. So even if we compute the state faster than we expect or slower than we expect, it's gonna be at a set rate so that our data, so there's no interference between the time on error, which is the time it takes to transmit, and the time of computation. And instead it's like, it's regimented to never cause a backlog of data that's not being sent. For experimentation, we need to determine the T latency, which is the time between you transmit from the rocket to the time that we receive it, and then execute the motors, which are controlling the rocket tracking antenna. So from testing, we can determine that. We don't need to do a launch test. We can just do any ground testing because the distance shouldn't matter. It's a very fast transmission time. So once we determine that, we can then figure out when we take our state that's computed on the rocket. We can also do an extrapolation of what a state will be in the at a future time, and that time will be T latency, which will tell it the rocket tracking antenna, and that will know what that will decide how far ahead the time has to point to match up with the rocket when it gets to that time. If that makes sense. This is our state machine. The main difference between this one and last year's one is that we're doing one-way reception. We're not doing, we can't talk to the rocket, it can only talk to us. So once we begin this process, it's gonna be autonomous. We can't tell it to like move from power on to launch ready or similar stuff. So the first thing we do is we power it on. That's gonna be a verification of transmission to the rocket tracking antenna. It'll give us the state name power on. It'll just tell us that. And it'll affirm this every second. We haven't decided yet how quickly we want to move on to launch ready. Or we were talking with the idea of buttons that can move us to launch ready. So we can power on, not use much of the battery power, and then switch to launch ready when it becomes time to launch. This is when we first begin seeing the state sent over. So we'll get the state name, which is the launch ready state, and then we'll get the rocket state. This contains all the sensor info, like the magnetic field of the magnetometer, acceleration, orientation, etc. It's also include the GPS coordinates. It's going to include the board temperature, and it will affirm that it's monitoring for flight mode. So the monitoring is going to look like a check for change in velocity over and over, and also a change in altitude. And once it receives that, we can move on to flight mode. Within flight mode, this has the motor burn phase, which will effectively, just to back up, everything within flight mode is going to have the same uniting actions by the flight computer, which is transmitting data, which is the rocket state, GPS coordinates, the same one as launch ready. But just make sure that for all these flights, we know that it's still transmitting this data. So it goes to motor burn phase, in which it'll stay like that, and just the only difference between that and the previous state is it'll tell us it's there. It'll then go to coast phase when it detects the acceleration rapidly decrease after both burns out. When we get to an approximate velocity of 0 and we can see an altitude decrease in the barometer and the GPS altitude fusion, we'll go to the apogee phase. This is when we'll begin the loop of the drogue deploy action. This will continuously loop until we see an acceleration change. And theoretically, if this doesn't work, the RRC3s will also trigger, which should progress this anyway. So we have this, so just to be clear, we have this trying to deploy to drogue. If it doesn't work, we'll have the RRC3 do it. Then we go to the drogue deploy phase. Then we're detecting if we're at the main deploy altitude. That's just a check over and over. Once we get to that, we'll do the main deploy phase. Similar to drogue deploy, there'll be backup RRC3. And that'll make sure that we get our main deployed. Then at the very bottom, if we see a spike in acceleration, we'll know that the main was deployed successfully. And then the last thing we do is we're constantly going to be reading for the altitude based on the barometer pressure and the GPS altitude. And that'll tell us when we're in the recovery phase. And then that'll simplify to just transmitting the GPS coordinates and the temperature. Once we get there, we can press the button to end this whole thing. Okay, the air brake computer is a little different. It's all the same PCB, and it's a lot of the same work we will do on the transmission computer. And by that, I mean like the way we calculate state for the transmission computer is the same state we want to calculate on the air brake computer. The main difference is we have no LoRa transmission capabilities. This is all internal. So what we'll do is we'll determine the rocket state, and this time instead of calculating a position at time T latency, we'll calculate a predicted apogee. That's based on when we predict the velocity will be 0. We'll determine the air brake extension necessary to hit the goal based upon the current state and the predicted apogee, And then again, this is all reused from our work on the transmission computer. The development, this will hopefully be finalized in the ESP IDF. It'll start with Arduino because it's what we have working, and we'll build towards this. The sensor modules are the same with using a combination of custom code and existing libraries. For onboard data processing, this goes for both the previous board and this one. We're going to use a combination of extended Kalman filtering for the best estimate of our data. And what we need to develop in order to do that is a model of our rocket, like a physics model using like Newtonian mechanics. So what we'll do is, we haven't done this yet, but in the process of making this model, we also need to deduce what assumptions we can make. Can we assume the rocket's always pointed perfectly vertical? Can we assume that it exists in a 2D plane? Like, there's a lot of things we need to figure out for that, but what we'll do is we'll apply this Kalman filtering, compare it to our model for flight, and then from that get a best estimate of our state. Again, this is the same process we'll use on the flight computer, which is great. So if we get one working, both working. But unlike the transmission computer, if we determine that a sensor fails, we can continue to send down transmitted data because we still want the data like for visualization on the ground. We might not have the rocket tracking antenna operate anymore, but if we detect any sensor fail on the air brake computer, it immediately sets the air brake into termination state. So the plan for the air brake computer is we're going to use CFD and simulation to create an accurate model of the rocket's trajectory and simulation. And the goal is through using Simulink or through using OpenRocket, we can get a simulation of a rocket's trajectory, which we can verify by a launch. And once we have that, then we can use the simulation to figure out all the things we need to do to determine how our air brakes will operate. And then in addition to that, we need to create an accurate representation of how our air brakes drag coefficient can operate as a function of extension and velocity. And that'll be from CFD, which a lot of us are working on. And ideally what we'll get then is, I'll explain in a few moments, like a table of sorts that'll tell us if we have a rocket state and we know what it's supposed to be based on our Newtonian formula, what drag force we need to slow ourselves to the goal state. And so in order to do that, we need to know our drag force and our drag coefficient, which will be found through CFD. Okay, so from the extended Kalman filtering, we'll have a rocket state at T burnout, which is basically like when the motor stops firing, which is when the first time we can begin to implement air brake extension. So at that point, we'll have an iterated upon state that should be accurate. And as I mentioned a moment ago, we can use classical mechanics to project our data forward and determine a state when the vertical component of velocity will be 0, which is the apogee. So until this point, our Newtonian representation can be a consideration of just the gravity vector and the net rocket drag, in addition to what a rocket is. And so this drag is dynamic and it'll operate as a function of extension. So what we're doing is we're taking a 2D lookup table where we input our state's velocity or Mach and our extension. We put in our velocity and we get out an extension because we know this the force we need. We put in our velocity and we get out an extension to give us the force we need to slow down to the target apogee. So the idea is that, so if we have this representation of our rocket formula, we can then determine the force we need to slow down to our target goal. So we plug in the force, we plug in the velocity, and it tells us the extension we need to slow ourselves down. So to do this, we'll be computing an error between predicted apogee and the goal apogee. And for this, we can use a lookup table, or we can compute the air brake extension necessary to alter the equation of motion to hit the apogee. And we're still figuring out which one we'll use. This is a general look at what the state machine will look like. We have the initialized state. So for each sensor, we're going to establish a connection between them. We're going to read the data. We're going to confirm that it can read data. If this fails, we'll immediately go to termination state, which is state 4. If this is successful, we can move to standby state. And this is similar to the transmission computer, where if we're not reading acceleration, we're not reading a change in altitude, do nothing. But once it reads this, we can communicate that, and we can begin to read accelerometer data to determine the end of the boost phase. Once we determine the boost phase is over, then we can move to the flight control state. And that's where we're talking about leveraging the data we have to compute how much the air brake should extend. And then through all of this, we're checking to make sure everything's operating correctly. And if it isn't, we can move to the termination state. The termination state will trigger no matter what when we reach recovery phase. And that'll be, as you mentioned, we might actually terminate during the apogee. And we'll work on that if we want the air brakes to be safe when we land or not damaged. Moving on to rocket tracking antenna or focaccia. This is our receiving antenna or a Yagi. It's connected to an RF module and MCU that's on the ground. this microcontroller will decode the state that we get because we're converting it to bits, so it'll turn it back into a state that we can work with. It'll then deduce the azimuthal and elevation and calculate the motor movements required to move to the location at the time t latency. And right now we're developing a counterweight system to combat the static torque. The antenna we have is huge, and so we want to be able to hold a position without stressing the motors. And in order to do that, we're going to do a counterweight. As I said, focaccia is a one-way reception with panini. The origin coordinates are inputted into the tracker, and it might not seem like it's necessary for a GPS on this because we can just plug in our location at the launch. But what's crucial about tracking the rocket on the ground is that we need to have a unified clock. And thankfully, the GPS module has a clock in it. So if we have two GPS modules both synced up, using a clock, we can know T transmission compared to T latency and have an accurate read of that. As I said, the receive state is used to compute the azimuthal and elevation of the tracker. This is done through coordinate conversions and trig. So if we know the coordinates of it, we can convert to a relative coordinate plane, and then we can just use we can relate their vectors to find the angles between them and compute how we need to turn to that direction. To know the position of the antenna, where it's important that we're using rotary encoders on the output shafts. So this makes sure that no matter what our motors actually do, we know what the execution was because we have something reading the output shaft, and those are going to be the rotary encoders. The purpose of this whole setup is to send the commands from the transmitted data to the stepper motors to adjust how it's angled. And then once it's done that, we can take the same data and send it via wire to the ground station for displaying purposes. And then the ground station will be displaying our red data from this and then Ben's camera feed, which will be awesome. And then this repeats. Riley is working on the PCB for this. We had a breadboard, but that just wasn't feasible because it fell apart consistently and I don't know, it wasn't a great system. So we're working on a PCB for it. This is going to be mostly a PCB of ports. And what I mean by that is all the components that we need for this rocket tracking antenna are going to be located on the actual apparatus, not on the board, because we need to know, the IMU relative to the orientation. The IMU relative to the orientation of the antenna to make sure we have accurately represented the gravity vector and the magnetic field at the point of the antenna. And then, so what we'll do is on this board, it's mainly ports to reach off from our breakout sensors to the board and then connect to the MCU. We're also working on a step down, which Riley's working on, which will convert our battery power from being used for motor supply voltage to a 3.3 voltage for logic. The ground station is called Jabata. It'll display the real-time data on the dashboard of the rocket. It'll save the data to storage as well for future analysis, and it'll read us these statuses that we're reading from the rocket. And this is independently powered along with the rocket tracking antenna, so they both have their own power systems. Ben, you want to come up in a second?
Yeah, I mean, so I can talk on this.
Stop here,
Yeah, so basically the ground station is the same exact concept from last year. Just hopefully adding, as Matt said, the additional live camera feed. Construction and everything is staying the same. It's being powered by a Raspberry Pi along in a plastic case with a contained keyboard, mouse, and everything that we need to sort of interface with it. We'll be using lithium-ion batteries to power that. It says it on here. We'll be stepping down 5 volts. I think we're stepping down 11.1 volts down to 5 volts. For the Raspberry Pi, we still have that board from last year, and that'll follow similar construction in terms of delivering power to our rocket tracker. Matt, if you want to go next slide. Sorry. Obviously, there you can see the construction. We're planning on 120 watt-hour lithium-ion battery just because the the steppers that we're going to be using have a decent amount of idle current, and just this computer being out all day is going to eat through a lot of power, so we don't want to be sort of stranded at competition with no power on this. But yeah, same thing, just using a efficient Raspberry Pi to run the thing. And this, go a little bit more into the batteries. Same plan as last year. We'll be wiring it out of 18 650 cells. That is not a number of cells, Nico. That is a specific type of battery cell. We're going to have 12 of those wired together for a voltage of 11.1 volts. And as said, total capacity will be about 120 watt hours, more than enough power to power the ground station itself, as well as anything that's running off that, like the antenna trackers. Yeah.
Right. Yeah.
Hey, I remember looking at these when we were looking at powering the nose cone IMU board, So don't worry, I got.
I also want to make a brief aside here. We're talking about using the drone to like visualize how our board operates if our sensors are accurate. We actually will not need the ground station to be ready for like data visualization purposes. One of our members, Lewis, found this thing called Foxtrot, which allows us to visualize data. So that's all like a pre-made system, and all it does is it takes raw values and actually does all the work for you in constructing. Like honestly, like in like almost a Google Maps type sense, what your trajectory was and what it looks like in 3D. So with the drone, we could use that before we even have the ground station up and running to visualize if our data was accurate or not based on what we saw and what the computer tells us, and like live updates too. It's really cool. Plan analysis to make sure that our transmission is operational. We're going to do a link budget computation for making sure that the antennas can operate within the AV bay. We can do, actually, we'll probably just do testing. We won't do simulation. We can just do testing to see how it operates. So we'll do AV bay range testing. For sensor calibration, this just involves software online where you make sure the antenna, where you record data for like, I remember Daniel and I did this last year, for an IMU or a gyroscope, you can just orient it in every direction, compare it with the magnetic field in your location and what the outputs should be, and you can calibrate your sensors that way. The issue is we've also to do this in the AV bay to represent flight conditions. So we'll have to do this entire like orientation movement in the AV bay, which we'll figure out. But thankfully we can just make sure we're doing it correctly with the software. That'll just be something we do. For state transition simulations, this will be something that we work on a lot more this spring. If we can get an accurate simulation of what a rocket should be doing, then we can effectively see if our air brakes trigger at the correct time based on the simulation, and then based on a second simulation, which is testing what our simulation should be, and then we're also feeding it in this air brake extension. It can tell us if it was successful in making sure we hit our target apogee. That'll be something a lot more that we get a lot more into in the spring. Further testing, we just have a ground station process. Does it like work correctly? We can just feed it data and see if it works. For interactive science, I mentioned we have range testing. I don't know what that one is, but we can make sure that the state machine works, as I mentioned. It's kind of repetitive. Okay, so for the risk matrix, the biggest risk we would do would be triggering the deployment early. This would occur if we read false data from any of our sensors that tell us we're at apogee or not. And as a result, we trigger the charges and separate our rocket. This would be a massive problem. So to do this, we'll run simulations to make sure it doesn't occur. We're also going to have systems in place that check multiple inputs from sensors before determining if this is necessary. So like for apogee, we'll detect is velocity approximately 0, and also it has altitude begin to decrease. We're not just going to rely on one, because then if it spikes or hits a random value, we'll trigger this preemptively. There's also recovery deployment fails with sensor filter and sensor fusion. This can be fixed by just optimizing the filter parameters. We can verify each step of their algorithm for outputs correct values, and then again, this will be backed up by the RRC3. So we can ground test the RRC3 to make sure that if our recovery deployment doesn't fire, the RRC3 will still fire. We can make sure it's working by just testing on the ground. Telemetry offs and rocket tracking antenna failure. This can be due to a bunch of different reasons, but the main thing that we'll do to combat it is just extensive testing. We'll range test it, we'll do link budget computations, and we'll also test it at every orientation that the rocket can be in, or sorry, that the rocket can be in. The problem is kind of once the rocket tracking antenna loses connection and it falls out of sync with it, it might not be recoverable. So at that point, might better just take over manually and track the rocket with the antenna manually. So to combat this, we'll just do testing. We'll do range testing, orientation testing, all of that. Failure to save local flight data, petaflight local storage. We haven't had this problem yet, but we just make sure we are interfacing with the SD card modules correctly and make sure that just through testing it's operational. Again, as I mentioned in 3, the rocket tracking antenna loses line of sight and cannot realign. This will just be done by extensive experimental testing. We can do this not with the rocket, but also on the ground. Like if we have someone walking around a field with the board in hand, it'll work just as well for testing this. It'll be better for the AV bay to be walked around, but also just for more general testing without the AV bay, we can put on the drone. We can fly it around and make sure that it can track objects moving much slower than a rocket would before moving onto the rocket itself. There's a chance that when we decompress telemetry data, it doesn't result well, and there's also a chance that we lose data. We lose parts of the packet that's transmitted. So to make sure we do this, we're going to make sure all the data is sent in the same manner, but also have protection for the fact that if a data packet is not transmitted in whole, we have signals that signify when a new packet starts, or when the we have signals that we have information in the data packet that signifies when a new packet starts. So that if we miss part of a packet, it doesn't think that the next packet is an extension of the first packet. If we fail to save telemetry data to Chibata on the local database, we can try to work harder towards making sure that through testing it works. But also we have found the redundancy that which is if it doesn't save on the computer, we'll have it sent down to the ground station where it should be saved. If it's not saved on either of those, we have the airbag computer which will be saved. And that gives us 3 sources of hopefully accurate data. And if we add the IMU to IREC's payload, that'll also be another thing that's being saved. So we should have a lot of data to work with once we get a successful flight. And then the incomplete or non-user centric dashboard. I mean, we just I don't know, experiment with how it operates. Make sure it's most helpful to visualize. And that just comes working on it. Open issues. The flight computer, we need to make sure the sensor reading is accurate. We don't know if we know we were sampling at a way too low rate. We also never toyed with making sure the sensors read at their own unique rates. We also were reading some not great GPS values, so maybe it lost the GPS connection because at one point I just read 0 and then NAND. We also need to calibrate our sensors. We didn't do that for the first flight, so we'll be doing that for the next one. This will be done both outside the airbag computer, outside the AV bay and in the AV bay. We need to tweak the state diagram to account for how we'll move from the power state to the launch ready state. We need to tune the transition parameters. This will be figured out in January and February when we do range testing. We need to make sure that it operates at our range and at a speed that is most efficient. So the higher the frequency we can transmit data, the better, but we still can't have a backlog of data. For the ground station, we need to set up the ground station database and complete the physical design. For the rocket tracking antenna project, we need to mainly start getting the efficient counterweight system in place and start fabricating it. For the airbag computer, there's some worry that the computational stress needed to compute the airbrake's predicted state and then also determine what the airbrake extension necessary is. So we'll just need to make sure that our MCU is capable enough to do these computations and also collect data. If it's not, there's other solutions where we can have a second one dedicated just to computations. We need to determine a predictive equation of motion for our extended Kalman filter. What equations can we use to simplify? One team I was observing had a bunch of good insight into this. They were able to make a bunch of simplifications that made this equation of motion much easier to model. So I'll look into that and we'll look into how we can do that. And then we need to flight test to verify our simulation results. This is necessary to even begin the creation of and the tuning of the PID. So we'll need to make sure that our simulation matches our actual flights, so that in Simulink or that in Open Rocket, we can make sure that when we begin to make our PID controller, it's for an accurate system. This will be finally confirmed with flight tests. All right, that was avionics. Any questions?
You want to go first or me? Okay, so me. Okay. Well, first off, good shit with the antenna tracker. That sounds really, really cool. But going back to slide 136. So when it comes to determining, okay, so one thing to clarify, when we're talking about state, are we talking about the state of the filter, as in the vector that contains each of the different values that we're trying to estimate of the rocket? Or are we talking about the state of the rocket, as in like coast phase, burnout phase, powered flight
No,
phase?
we're talking about the first thing. We're talking about the state of what the rocket's orientation, velocity, acceleration, and position are when I say state. Okay,
so for the SRAD, why Mahani over an EKF?
That's a good question. We haven't chosen Mahoney over EKF. You know, I don't know. We'll try whichever one is easier and gives us good results. But also, I may have made a mistake. What will happen for the transmission computer? What will happen for the airbag computer will be the same process. I just wrote Mahoney for one, and I wrote EKF for the other. It'll be the same. So whichever one we determine to be better, which I'm leaning towards EKF, would make sense. I just wrote EG Mahoney for an example of what centrifugation could be.
Okay. Next slide, please. Okay. Oh, wait, maybe it's not that one. Next slide. All right, maybe it is that one. Go back. So yeah, you were talking a lot about. I'm gonna be honest. I could not follow what was going on with the whole optimized frequency and
Well, let me explain that better.
yeah.
Okay, so like every sensor should be read at a frequency that makes sense for what it's measuring. So for barometer, that can be read at a much slower frequency than our accelerometer or our gyroscope. Like those sensors we want to have accurate values for, so we're gonna read them. When I say read, I don't mean like send or like transmit down or anything. I mean like we have this state that we're updating with all of our data.
Yes.
And it's going to be updated with certain parameters more quickly than other ones. But then what's uniform is well, that's not how it is now. That's what we're pointing to. How it is now is it's all going to be computed at once. But ideally, every sensor will be optimized to feed data at a unique frequency that makes sense for that sensor. And then in general, we'll transmit at one larger frequency down to the ground station. That'll be at a much slower rate because just time on air and transmitting the waves just takes more time. Does that make sense, or am I explaining it poorly again?
No, that makes sense. I wanted to clarify that because I just wasn't sure if with Mahoney that is impossible. But with an EKF, when you're doing the state prediction, you could also predict the state and then you would update it with the measurements that you get from the sensor. So yeah, that makes sense.
Yeah, EKF is the one that I know more about. I should have put Mahoney on the slide. Sorry, we're not even using that.
Okay. Only thing about that is, are we still doing continuous polling?
Continuous polling from?
As in, like, you have a bunch of sensors connected to I2C and then you just grab them all at once.
No, I mean, that's how it is now. The idea would be that we grab from each, like, if every sensor is operating at its own frequency and it's updating its register with the most recent data, we're grabbing from each of those at a unique rate and feeding that into the current state. So it would not be pulling at the same rate for all of them.
Okay, then. So they're kind of like operating on their own threads then, essentially, right?
Yeah, they are operating on threads. I think that might mean that, like, I haven't executed yet on the Arduino IDE. That might mean it's impossible on that because I don't think it can thread. But yeah, that would mean they're all operating on threads.
No, you could thread. The Arduino IDE is also based on FreeRTOS, but the Arduino IDE is dog, so I wouldn't use it. Just use the ESP IDF. What else? Yeah, so then going back to that, I'm a little concerned with your sure, it makes sense, pull each sensor at its own frequency. I would just suggest that you still have some set delta T that you're updating the state at. Yeah, this is gonna be a lot of like semaphores, a bunch of weird checks that you're gonna be doing, but I think it's definitely possible.
But
cool. Next slide.
Also, sorry, go ahead. Never mind.
All right, next slide.
Next slide.
Yep. All right, maybe not that one. Well, yeah, actually,
I'll ask questions on that one.
Yeah, no, I was just a bit concerned. How do you guys deal with, like, sure, you have a filter to kind of clean out your noisy data, but generally speaking, how are you dealing with uncertainty in your measurements?
I don't know if we addressed that yet, but the idea, the idea that I had was that I don't know if uncertainty is. I don't know if this answers your question, but we would have this model of how a rocket should fly, which we are always comparing it to when we do the extended Kalman filter. And what that does is that I think that, I don't know the library, but like I think what that does is that accounts for the uncertainty in the sensor measurements. Are you asking like how do we determine the uncertainty in each of our sensors? Or are you asking how we deal with it?
It's more so, I guess what I was trying to allude to here was like, how do you deal with the uncertainty in your, I guess, your sensor outputs that you're then applying to this state determination algorithm that you got going on?
I think it would be dealt with the Kalman filter, right? Or is that not, would that not be accounted for there?
I mean, it does clean up the noise, but there is some degree of, how accurate is this filter estimate? How accurate is this state estimation? You know, I mean, you can assume that it converges to what it actually is after some time, but I'm just curious if you're just thinking, okay, let's use this filter and then everything should be okay.
I think
That's what
what
you're saying.
Daniel's getting at is that Daniel and I had a lot of conversations about this last year when we were trying to figure out the state machine as well. But for some of the transitions, like it ends up being where you want to your filtering has to be good, but you can't like over filter it or you don't get good enough data. But if you under filter it, then you leave yourself at the mercy of like just a certain amount of noise in the data. And so it's like, how do you categorize like the amount of noise you have and account for that in your state transitions so that when you transition from one state to another, especially from like coast to apogee or motor burn phase to coast phase, whenever you're ready to, sorry, coast to apogee, you like, yeah, you when you switch to apogee, you know you're actually at apogee and not either ahead or too far behind. And also for the more important side, you don't want to accidentally get into launch ready or into like motor burn if then the like transitions from those phases further onwards aren't maybe as rigorous because then like small variations you could basically go through the entire flight while being on the pad and then pop the nose cone off on the pad and then be very sad.
Yeah.
Yeah, I hear your concern. I guess it'll be an issue that I definitely look into. I don't have a good method for accounting for the uncertainty in the data, but I will look into it. What's good though is instead of computing the state at every point, we're hopefully going to be iterating on a state that's been computed since launch ready. So maybe that'll help with that, but that's an issue that we'll definitely look into.
Yeah, I think the worry with iterating on the state that's like been already computed is that if one state transition fails and like cascades to the like if one state transitions when it's not supposed to go, then you're already at the mercy of everything else down the line. Whereas like if you have checks in there every once in a while, I don't know, like an altitude lockout or something, might add another safety.
Yeah, that's what you're saying.
Sorry, Daniel, didn't mean to interrupt.
Maybe like an expected state for what it should be at certain changes and compare to that. I don't know.
Sorry, what?
Oh yeah, that could work.
I guess I'm just.
Daniel is hard of hearing at his old age. It's okay.
Oh, did you not hear that?
No, it's cool. I'm good on this slide. You good, Nico?
Yeah, I think I'm. Let's see. I had a question written down. I don't remember.
This is where a button would go.
Yeah, I'm good for now. I'll come back to this later.
Button addition is good. All right, next slide.
Oh, sorry.
Okay, yeah. So that I was curious. Are you guys not making use of GPS updates for your sensor fusion?
So, okay, so we definitely are using GPS updates in our sensor fusion for the transmission computer. The issue is the computer that is in the air brake section. I don't even know if it can get a satellite lock. Do we know that? Is it surrounded by fiberglass or surrounded by?
Both of the bulkheads.
Okay, so I don't even know if we can get a satellite lock. If we can, then we'll use it, but I can't guarantee it. But I've read that it's possible for a different team report that you can actually get good values with just based on integrating an iterated state and also reading the barometer. I don't know. That would be what we go with if we can't get a GPS lock.
It's possible, but you know, GPS is just really reliable. There is forgot. I believe it's possible for you to kind of no, that doesn't work. Yeah, no, never mind. That doesn't work. Yeah, if you don't have a fix, it might not be all that helpful. But I mean, I would just prioritize if you can get GPS, it would be good to have that in, and then in your filter, try to make it so that the what is it? Process measurement noise covariance matrix prioritizes that. And and honestly, if you're using an EKF, just go for, I would make it so that it's more dynamic. So then if you don't have a GPS fix, you can pretty much deprioritize all prediction updates based on it and rely solely on the IMU and barometer measurements.
Yeah.
Also, make sure the GPS doesn't pull your filter, like cause too much lag in the final comment filter stuff, just because it's kind of slow.
Yeah.
I mean, I think that's easily, it's the same kind of issue that same kind of thing that Matt mentioned before, where they have all the sensors at different sampling rates, so they'll update it when there's new data from the GPS module. Update the prediction when there's new data from the GPS module. Yeah.
Yeah, I think once you get closer to apogee, that works out nice. It's just during the like initial liftoff coast phase where like it's likely to be over by the time the GPS update comes.
Yeah. Yeah, I think
Anyways,
I'm
carry
good
on.
here. Next slide, please. Oh yeah, I was just gonna ask, you were mentioning EKF and Mahoney, but you said that you're just going with EKF, so it's cool. Next slide.
And if we crack it once, like we're using 3 things that I'll be using, it'll be like, yeah, it'll be cool.
Okay, all right. So when it comes to, so these are pretty much your two, the two algorithms or like methods of deploying air brakes that you've been thinking of, right? With option 1 and 2.
Oh yeah, yes, that's correct.
So I'm gonna be honest, option 1 is a little freaky. I mean, personally, like when I think of air brakes, I think of a controls problem where you have some sort of closed feedback loop. This is just, you're using a lookup table, which I think, which makes sense when you're dealing with a problem with a lot of nonlinear terms, but you know, if you're dealing with a bunch of nonlinear terms, you would want to have more experimental data than just, you would want experimental data, not just sims, you know?
Yeah.
So for that, I'm more in favor of option 2. If you could go to the next slide. Yeah, I was in favor of it until you mentioned another lookup table.
Well, here's the thing, we need to know, we need to have some database that tells us, you know, how our velocity and our required drag correlate to an extension. You know what I mean?
I mean,
yeah.
No?
I think we should not just do
Like
PID
if you-
on the estimated bounds.
Yeah, okay, yes, that would be.
I think that's kind of what's more expected right now. We just use some the controller based on just our output. And then just adjust dynamics based on that.
Yes, but we would need.
I have no idea what you said, Lily.
That was May. That was another.
May was saying that this is a controls problem, like we should be able to compute this information ourselves without looking it up based on our state and our predicted state, which is true. I thought there's a part where we would need some sort of information about relating extension to like the
No, I
Oh
said
no, absolutely, yeah. I agree with that.
in terms of like, you want to
Male
say
solutions.
if we want to calculate, like if our PID calculates that we need some negative, you know, velocity, then we need to say how we see. But I guess also is that not included in just the calculation of constants like PID tuning?
yeah, but then like how does that tell the motor how to move, you know?
I mean, that would just be like you're kind of
Unless we have a pre-made relation between motor movement and
Oh, is this the air brakes meeting now?
this is what people like.
Oh, second one.
That's crazy.
May's got a point though. Yeah, you'll get better control if you can do PID or like some form of closed loop where you do something and then you see how that changes your prediction and then you can adjust for that. The downside is you need to basically be like running the sims on board, or your lookup table has to be so massive that it takes into account all the options for altitude, vertical velocity, horizontal velocity.
Yeah.
Yeah. Yeah,
the
I'm
problem
a
is,
big
like,
fan
we
of the
don't have,
closed
like, we
loop.
don't get an accurate sim and like we don't have much launch testing, how can we do the PID, you know? And like, that's why option one seems possibly more feasible and it seems easier. Then again,
That
it's
is true.
That's true. Yeah.
You could even maybe just do like PI control even. Like
yeah.
or like a
So we what the hell? Okay, so we have our observer, which is the EKF. So and your controller is just PID. So I'm curious how you're going to deal with saturation and wind up.
Say that again?
Saturation and wind up. You're using a PID controller, so that's going to be like a bit of an inherent problem that, or just some kind of thing that you'll have to take into account of.
Yeah, I had not started to consider that, so we'll look into that. That's why option one sounded more better. I don't know.
Okay. Next slide, please.
I have another suggestion before you move on. You also can calculate the performance of, can you hear me?
Yeah.
Yes.
You can calculate the performance of the motor and use that to guesstimate, because you have, the motor has a predicted performance, right? And you can know what range of that performance it has and use that. And that might put a set number of seconds to try to get closer if you're not really going to do full PID. It's another lookup table again, but it's, you're only deploying it. The only thing you're changing when you're going up, you're not, because you can't, turn on the flaps when you're powered, so it's unpowered. It might be easier to just try to guess it from that, and the second the burn stops, like start calculating how much time do we need to put the flaps out. And once it's on a solution, just try to do it.
Oh, doubling up on that? Yeah, it would be a good idea to check your rate limits. Like, you don't want to slam the servo from 0 to 100% in 20 milliseconds,
Yes, that is true. We're also working on how much torque we need to fight against with the servo and what is even possible for that.
that one should be just like drag on the plates plus free body diagrams, right?
Yeah. Oh, that's what I wanted to ask. Did you guys start with the free body diagram at least?
Say again?
Did you guys start with the free body diagram?
Yes, sir.
Oh, wow.
And we calculated the friction. That was our main driver of the torque. We got a very low number for the torque required. So it's something we're gonna have to validate once we actually build the physical system and can actually test it with I don't know, hanging weights on the plates or something like that to emulate the conditions.
Sounds like a great test setup, I suppose.
Okay. Actually, yeah, next slide. Skip to 148 actually.
What's next slide?
Oh, it is? Oh, shoot. Okay, yeah, so the issue I have with this is you're using RSSI as feedback. When I think what you were thinking about with this problem was it would essentially be something equivalent to a Marco Polo type of thing. But, if you're yelling Marco and I yell Polo, you get not only the magnitude, but direction of where I'm yelling. With RSSI, all you're getting is magnitude. So that doesn't really give you much of an idea as to, yeah, vector. Yeah. RSSI is just a scalar value, so it doesn't really help you with figuring out where you should be moving your antenna.
Okay.
So yeah, come up with a different feedback mechanism for handling that. Honestly, I don't think it would be much of a feedback mechanism. You're just trying to read the GPS coordinates of the rocket as quickly as possible and just moving your antenna straight to that.
Yeah, but we're also trying to figure out actually where it will be and move the antenna to where it will be, not where it is. And that's based on T latency. Well, T latency plus where the rocket's traveled in that time. Well, yeah, T latency.
Yeah, I think most of your latency issues will only apply at the powered flight phase because that's when your, I guess the antenna is moving a lot anyways. You have a large degree of freedom. Well, I wouldn't say large, but you have a good degree of freedom even if you're using a Yagi.
Yeah. I think the latency would come into play with like the computation. I don't know. It shouldn't be that long a time. Like it'll get to the attack rate.
Yeah.
I don't know.
All right. I think you should go to the next slide.
Sounds good.
Okay, skip that one. I think I'm done, actually.
Okay.
My turn? Or do you have more?
It's your turn, you go.
Second.
Okay, sorry, give me a sec. I was trying to finish my lunch before Daniel finished, but I didn't. I was unsuccessful. Could you go back to slide 135, please? Also, same thing, fantastic job so far. I'm really excited about this. The air brakes are going to be super cool, regardless of what control method you end up using. And it makes me so happy to see that we have plans for ground stations and cameras and all these boards and all this data. It's a far cry from what we had on the Karma a long time ago, so you should be very proud of yourselves for that.
Thank you. There's no slide 135. Somehow.
Wait, what happened? I swear, I wrote down slide 135. I was
136.
okay.
I mean, this.
These dimensions showing.
Oh no, I'm cooked. Next slide maybe? The slide, I heard someone talking about a fan and cooling.
Uh-oh. He's getting old, guys.
This is the only fan we've talked about.
Are you talking about cameras?
Maybe? Okay, I don't know why I wrote 135 then. Anyways, yeah, no, so the concerns with thermal, I think it was Ben, someone was talking about using natural convection inside the av bay to cool the cameras. I just wanted to check if sanity check that the av bay, the air inside the av bay will be able to change and refresh with the air outside the av bay quickly enough. Because my worry would be that it gets, if for some reason it isn't able to escape and be replaced by other air, that it increases in temperature and increases in pressure and messes with the barometer, even if just a little bit. So I just be wary of that. That might not be an issue at all, but just, yeah. Okay, 138. No, I don't know if my slide numbers are going to be right, but okay, yeah, 138. Daniel touched on a lot of the stuff I wanted to talk about, but I think so. My first question is, what's the contingency, or that arrow between power on and launch ready? What are the plans for that right now?
Okay, so that would ideally be a button. Before it was changed to this, we had the idea that the ground station could communicate with the flight computer. So we just press a button on the ground station, it would give the information to move forward. Right now, it's nothing. It could be a timer, which is a great solution. So a button would be ideal. A button. That's my answer.
Okay, cool. Because I was gonna ask what happens if you do a button and then you can't the signal doesn't go from when you press the button.
You're saying a button on our end versus on the actual rocket?
Oh, I see. Okay. So button on the actual rocket would be something you press and then leave,
Sorry,
and
there's
it's
no
already
communication
launched
between them.
ready.
Like once the rockets, there's just no communication between the rockets, only receiving.
Okay, cool. Got it. I'm happy with that. And then for, I guess it doesn't really matter. If in launch ready, you're like recording and transmitting all the fields at the frequency you want, and
Yeah.
that's not too power intensive, then go with that. If it does become needed for you to like wait on the pad for a while, I was gonna suggest at least looking into this. I don't know if this is actually an option that will work, but having like a cache for a few seconds of the higher frequency data and then deleting that. I guess that would only do it with storage. But that way, if your launch your like detection of the motor burn phase um, gets kicked off, but your sampling rate is lower, then you can like go back and you'll have that data there. Yeah, that would help with saving space on the SD card, but I don't think that's a problem. But it could help with transmitting larger amounts of data. Like you could get away with transmitting like fewer packets until you know you're in the like rocket is flying state and then transmit at a higher frequency. But yeah, not as important. Yeah, okay. I think that's all I have. I just, want to hammer home what Daniel said about edge cases. I think, oh, and to give a little bit more clarity on what we were talking about earlier with the noise and like false triggers.
Yeah.
Daniel and I had looked a while back at implementing logic to like go based on the standard deviation of the sensor.
Okay.
And then like a normal distribution of standard deviation, like a standard normal distribution, pick a range of standard deviations away from that median, away from the mean. And then from that, you get like a percent chance that your data is within that range. And so if you're going at apogee and you'll have a little variation up and down naturally, but then once you have something that's like more than 3 standard deviations below what your like mean your running average up to that point has been, then you can say with higher confidence, oh, okay, now we're starting to drop in altitude. But yeah, lots of different ways to go about that.
That's a good verification method. And I think that doing 2 checks on 2 sensors would also be good. Like, are 2 things that would happen at apogee happening, and then also.
Yeah. Yeah, I think my worry is just like, you don't accidentally want to leave yourself at the mercy of 2 noise events happening at the same time.
That's true.
But yeah. Okay, slide 145, please.
Oh, just wanted to add
Faster
to
than-
that little thing. All of this was done making use of a weighted moving average to smooth out the data that we were receiving from the barometer. So
Sorry, I didn't catch what you said.
weighted moving average array.
Okay.
Okay, I wrote down here. Oh, yeah, never mind. We already talked about this. Slide 155, please. Sorry about that. 155, yes. Okay, planned analysis. Yeah, just wanna hammer home on this point. Obviously, you guys know this, but it is really important. The edge cases on this are super critical because if you accidentally deploy the energetics on the pad or on the way up, it could either be a danger to the people around you or just kind of tank the whole flight, and it's not very exciting. And because of that, again, want to encourage testing as early as possible. And same thing that I said a while ago, but I'd encourage prioritizing runtime on whatever boards we have, and like prioritize time that they're running code and gathering data. Just even if it's the most rudimentary setup, even if it's just on a table and like moving around and whatnot, because I promise you in the like first few sets of times that you're doing that, there'll be plenty of things that come up and plenty of like bugs you'll be able to fix and like quirks with the data you'll be able to see, and edge cases you'll find that you'll be able to sort out on the ground. And the reason I hammer this home is because I know we got caught again and again in the trap of the rocket's not ready, or like we can't do an injection test, we can't do a ground test, we don't have a setup for this. Highly recommend just prioritizing plugging it in and running it, moving around, getting whatever data you can, and looking at that data as early as possible.
Yeah, definitely. We want to make sure that our data is accurate, and we can do other tests like that. And that's where the drone would be helpful too.
Yeah, for sure. Yeah, and like not just like having the data accurate, but also making sure that you can get the data and that it looks even within the realm of what it's supposed to be.
Yeah.
All right, that's all my old man rambling about that. Again, great job. Good to move on to the next section. Unless someone else has a question.
Yeah, one last question.
Yes.
I heard that you guys would be using Simulink for
Yes.
some of your control algos. Are you going to be using its code generation, or yeah, are you going to be using its code generation for the filters and the actual controller and all that stuff?
I don't know yet. We could. Right now, we're just seeing if we can get an accurate model, but we could end up doing it ourselves based on what we get there.
Okay, just wanted to mention that for the method that you want to go about writing this EKF, there's usually two ways of going about this, where you have your what is it? You have your Z vector, which is just your measurements, your big H vector, which is just a vector of matrices, which is where your H is the measurement Jacobian, and then your R matrix, which is your measurement noise covariance. One approach is to just stick them all into one big thing, like have all of your measurements just be in one big matrix. And from there you could, set your prioritize some sensors over others by, honestly, maybe I'll just write this up. This is kind of a messy. But yeah, I just wanted to note that caveat because I'm not sure how Simulink goes about with their code generation. I just wanted to highlight that if you go about writing it yourself.
Yeah, right up. Let me know. We can talk about it a lot more as well.
Yeah.
All right.
Ellen had to go.
Sorry for all the questions.
Does that mean we're done?
We'll just go over it.
Hello again.
Oh.
So for our launch, we're gonna launch on a 98mm diameter motor, 702 millimeters length. Short. We're launching Cicerone, but so ammonium perchlorate composite, reloadable motor casing into fiberglass motor mount tube, thrust plate. Load travels through the thrust plate from the motor into the thrust plate, and directly into the airframe walls. Yeah, we have a COTS Aeropack flange adapter bolt on the thrust plate, and then Aeropack COTS motor adapter. Oh yeah, for test flights, we'll fly on the 75mm diameter motors, but we'll use motor adapters.
Yeah, this is what our motor casing looks like. For the M3400, we're using a Cicerone Pro 98 4 grain motor casing. We picked this kind of a combination of our airframe size and other motor constraints. Like Cisco said, for the test motors, we have a Aerotech RMS 98 10240, and then we have the spacers and adapters necessary to make those size adjustments for anything smaller for a test flight 1, 2.
So motor retention, we have our SRAD thrust plate retaining in the booster by epoxy and spilled in the grooves using the grooves of the thrust plate for the bonding. And then we have a flange threaded motor retainer, which is connected over the motor thrust plate via 12 832 bolts. And then we also have the threaded motor retainer cap screws to motor retainer to hold the motor in place.
So this is our motor for the first test flight. It is an Aerotech L2200. It is 75mm 4 grain. Maximum thrust 3,114 newtons, burn time of 2.3 seconds. Total specific impulse of 5,104 newton seconds. It weighs 5.5 pounds and it will be a beautiful green color. That's what the thrust curve looks like.
Second test flight, M2400, Aerotech, and it'll be 3 grains, 98 millimeter. I know that. Max thrust of 3,401 newtons. Burn time of 3.2 seconds. Impulse 7,700 newton seconds, and propellant weight 8 pounds. And it'll be blue.
This is our competition motor, 98 millimeter bore grain. These are the values already mentioned. 2.9 second burn time, impulse of just under 10,000 newton seconds. It weighs almost 10 pounds, and it is a white thunder color with a backup of the CTI M1450.
Have you investigated how getting this motor or getting any accessory motor at this point?
We've talked to Rick, who is no longer working for Wildman apparently, but
Right.
he said that he can get it, I think, but he's not going to IREC, so we're gonna contact the people who are at Wildman still and see if they can source it. Because he said that he put in a big order of Cesaroni motors, Rick did, so I'm assuming Wildman should do the same.
So does he? It's so he doesn't have it, but he thinks he can get it before then.
Yes.
Yeah.
But
Do
then
you-
our issue is if Rick gets it, how do we get it to IREC because he's not going there?
Is anyone driving there?
Yes.
Yeah.
Yeah, but you're not allowed to do that. Okay.
Our car, but yeah.
Yeah.
Okay, hello. Like,
Okay. So what happens if you can't get it?
Well, we have our backup. We'll get some motor. We know that Rick has we had originally chosen. Oh no, because then we would have to create arrangement. We are contacting all of the motor sourcing people currently, and we will ensure that we have it soon. And if not, then we'll cross that bridge.
Okay.
But another concern with traveling to IREC with it is like temperature cycling because it's going to be in the summer, and then we would have to take it into all of the hotels that we go into, and that's not ideal.
Yeah. I mean, you could ask Rick about. I mean, if you can get it. If Rick can get it, you could ask him about whether he can ship it to Tim or something, and to Wildman or something like.
Is Tim and Wildman?
Tim Lair, if you could ship it to Wildman, they're definitely going, but I don't know. There's other possibilities, I suppose.
Okay. We tried our hardest to get Aerotech, but IREC is really cracking down on Sparky motors this year. So.
No.
They're not allowing Sparky motors?
Not at all,
That's
no.
annoying.
Yeah, we were originally planning on using a Sparky, and they kind of shut us down. So we had to pretty quickly pivot, and it's pretty much the majority of Cesaroni is kind of in that range.
It kind of turned out well though, because this is a shorter motor, so we can shorten the booster, which moved the air brakes down, which like increases stability after air brake deployment.
I mean, I think Cesaroni's are good motors. It's a fine motor to use. The concern I have is just that I know that Aerotech is making motors specifically for IREC to ensure that you get them, and I don't think Cesaroni's doing the same thing, and that's the issue.
Yeah.
So my suggestion would be to get it. You'll have to figure out how to get it out there, but my suggestion is to get it as quickly as you can.
Yeah. Our understanding is
just
that
to
Rick-
ensure that you've got it.
Rick seemed hopeful in his ability to obtain the motor.
Yeah.
So it is probably just a matter of getting it there, but it is an open issue that we'll.
Okay.
And yeah, the hazmat shipping might be expensive, but I think FedEx can do it. Like, I think you guys could take the motor to FedEx and be like, this is packaged the right way.
The thing with
Maybe not.
with hazmat shipping is to send real hazmat, you have to have training and stuff. So what you'd want to do is have Rick do it, because I'm sure Rick can do it.
Yeah.
But you can't, usually individuals can't send hazmat.
Yeah, okay, well, we'll have another conversation about that.
Yeah. Okay.
Yeah, thanks for the correction. Sorry about that.
Yep.
Last quick thing. I'm a little worried, to like Sam's point of not being able to get the Cicerone. I'm a little worried about the 1450 being the backup. One, because it is Cicerone and might be hard to get, so it would be nice to have an IREC as a backup. But also, the off-rail velocity is going to be quite low for that. For the M1450, so that would probably, I don't know if there's anything where you could like push it a little bit higher, and then right now the only part on the rocket that was acceleration limited was the payload bulkhead, and even then it was like not far away, so you could probably beef that up. I don't know, up to you guys.
Kind of on that note, yeah, that's an open issue. IREC's very strict about their off-rail velocity this year, which is kind of it's another reason why we had a lot of trouble finding a motor that would get us off the rail fast enough and be able to get sourced and fit. So the 1450 is close to their minimum 82.
Don't we still have 2 pounds of payload that we have to take off?
Yeah, the simulation, the rocket in the simulation right now is a bit overweight, so we do think that we can get this particular motor to have the optimal off-rail velocity. But there is once again that issue of sourcing. So yeah, we're definitely gonna double down on getting a clear answer from Rick if he can get that or not, and if not, we are gonna reevaluate aerotech options.
Okay, cool. Sorry, I thought the minimum was 100. I didn't know they dropped it to 80. So they dropped to 82 and made it hard minimum?
Yes.
Yeah.
I see. Okay.
Yeah, I mean, there's just a very limited set of motors in that range. That's definitely an issue. I know, I mean, the other possibility, which I almost hate to suggest, is Loki does still make motors and stuff, and that's another one you could look at. But then you need a different casing and everything. So.
I mean, that's already an open issue because we don't have a 4-grain 98mm probe, and we can't use a longer because it doesn't fit because it's short.
You can't use spacers. Okay.
Yeah.
Oh, because we still had the car motor in the casing.
Well, I mean, not even that. Like a 6-grain case doesn't fit in our booster.
Oh, yeah. Sorry. Thought I said motor doesn't fit. Yeah.
So these are our simulations. We went over them in systems, and then this is the 1450 with the lower off the rail velocity, like you were saying, but also lower acceleration. And velocity. I don't know what you got.
Just strap a bunch of H-140s together.
So
this is our risk matrix for propulsion. The absolute worst scenario would be the motor exploding, likely due to an improper assembly of the motor, which is why we want to have those test flights to also get that practice again of assembling motors where we need to put together all the grains. We have a much less likely scenario, which would be the case is broken, but that's still a high impact, which is why it's in the yellow. Then we have 3 more risks, which would just be heat and pressure, stock and tolerance, which are all in the green. The next slide we can talk about.
Well, mitigation issues. What was it? Oh, it is.
So yeah, rapid schedule disassembly. We just want to get that practice to reduce that risk. Take our time during motor integration. Hopefully, an IREC will be able to be under a tent, have the time and people allocated to just getting that thing assembled properly. The risk of a broken casing, don't lose or break the casing. And we also need to procure that if we do end up going with the CTI 4 grain. Improper heat, pressure, protection, equalization. We need to make sure the liner is in good condition and the adequate pressure equalization holes are in place. That risk of motor casing out of stock, we're actively working on that, talking with Rick. We're going to double down on that. And finally, improper tolerance to motor hardware. We're going to do what we can to make sure everything fits together. This has been an issue in the past, but we've been able to work around it in past years.
Our open issues to stay in contact with manufacturers, aka Rick Wildman, to get our rocket and see expected lead times and how we can get it to IREC. Yeah, thank you. You have questions about propulsion or about anything?
So actually, I got a should 90 actually.
Daniel, what is happening there? He's talking to us from the great beyond. It's the like.
Daniel.
Oh, I said never mind. Did that not go through?
No. Yeah, I don't have any other questions. But fantastic job, everyone. Super exciting to see. I know how far we've come in the last 4 or 5 years, and there's a lot of work left to do, but it'll be hopefully a lot of fun, and hopefully we can get test flights and good data. But regardless of that, I know it makes me super happy to see all you guys continue to work together and continue with the new project. So thanks again for inviting me, and thanks for all the hard work to put this together, and good luck going forward.
Thank you.
Good luck, and let me know when you head out, when you're looking to do your test flights, I guess. So I should. I've been trying to get to the launches up in Vermont, but it's been between the bad weather and then when we finally do have launches, we seem to keep having seem to keep having other commitments, but hoping to get up there at some point.
Yeah, we'll definitely let you know.
Yeah.
Also an update to you, Sam, we submitted our PDR 2 days ago, or not PDR.
The progress
PDR,
report
the progress
Good.
report one.
They did extend that deadline by a week, but we're submitted and we're locked in and we are happy to be done with it.
Awesome.
Yeah. Any other final questions?
It's 5:04.
We're only like an hour behind what we thought. 45 minutes. I'm happy with 45 minutes behind. I'm happy with that.
Thanks for
Pretty
staying
good.
on.
Thank you.
How do you guys think this record compares to our last PDR?
Didn't we get it in like 4 hours last time?
You think you can go over the beginning part, entire beginning part that I missed again?
Oh yeah, May wasn't here. Go through slides 100 to 145.
What?
Yeah.